let's introduce the scene and the first system, which will be the firing system. All right. So here I've got a few cameras. It's pretty standard stuff. I've got a moving camera and a non-moving camera. Got a few objects that we would normally use to render with, but we can just ignore those for now. Let's see. Okay. Now, we mentioned scale earlier. Whenever I'm setting up a scene like this, I always have a little box to represent the size of a person. And let me see, where's my ground? Still getting a hang of this mouse. Ground. Okay. Yeah, sorry. Okay. So, this is the size of a person. And that's really important because that means that we would model all of our effects and everything to go based on that scale. Everything from gravity to particle size to mass to dynamics, weights, and everything. It's always just a good idea just to have a simple 1.8 meter high box just to see this is a 6 foot person. Really get a sense of scale as we're working with effects. So that's just a little trick right there. Okay. There's the ground. Okay. Digital assets for animation. Now, in a studio situation, you might not be so lucky. Often we'll have just caches of geometry that we're reading in, and we have to do something with them. So here we have just some digital assets for tanks. Now we can adjust these and reanimate them just to test out firing on different things and frames. So here's our tanks, and notice they've got a parameter up here, fire frames. So this is just a string. You guys all know what a string is? Yep, kind of. A string is characters, or a string of characters. So even though these are numbers, I find that the best way to represent any type of action that we're going to have to art direct is with a string of characters, and I actually haven't seen this done very often in Houdini, so we're gonna do that, and I guarantee you won't want to do it a different way afterwards. Okay, so here this tank is firing on frames 25 and 45, and this tank is firing on these frames. Okay, and they're just rotating their gun and moving around and stuff. To use these rigs, just do a tab and transform, and we can either select this and move it around. Yeah, I should hide some of these objects before I do that again. Okay. Let's see. Let's just start with the building model. Okay, that should be okay. Wow, what is that doing? Okay, there we go. So these are just animated, and we can animate these to change them and fire on different frames and everything. We also have a Jeep asset, but we won't get to that just yet. And the first thing we'll try to do is to make a firing system. So once we go back to our desks, just familiarize yourself with these tanks for just a few minutes. Just go ahead and hide everything else except for the ground and the tanks, and I'll be around to help and everything too. And then we'll just take a look at this tank firing system, and we can go inside and we'll just kind of make it along the other side, and always use this to reference if we get stuck or need help, or of course ask me too. Let me just show you guys what's going on real quick. Okay, so what this guy does, okay, so he's merging in the two gun tips from these tanks. And I've got a Python expression to get the correct objects from these arbitrary things, meaning how do we use Python to tack on stuff to the end. If you have a series of things in your scene that you always have the same kind of postfix to, then how do we loop through in Python and append strings and stuff? Some of you might know this, but for those that don't, we're just going to tackle it real quick. And then after that, we're going to explore how to use Python in a attribute crate and loop through and gather other things as well. Okay. So what this will basically do, there we go. Okay, so this will put the parameter from those objects on each primitive here, and then we're going to loop through and turn this parameter into a separate point for each firing event. So they come in as objects. We save a parameter on those objects to primitive, and then we loop through these guys and turn it to a point for each one. Okay, so after that, we have a point representing exactly what's going on in our geometry with an attribute of the correct time. So this is really, really useful, and it sure beats keyframing and putting stuff in scenes and things like that. Okay, so that's kind of on there, and then we're baking that. We're going to bake that in time. So now we have, see, 5 points, one for each firing frame. If we were to change one of these, so here I'll add another frame here. Let's do frame like 80. We see another point appear exactly when it happened on frame 80. We've got the normal, we've got whatever velocities were already present there, we've got everything. Okay. After that, we'll have a system that will see how it's only firing on the right frame at that point. You don't really want to go through and do a big loop on every time step. So notice this says time dependent no. Anytime we go through and we gather a system for all of these attributes, say we're gathering information from a crowds department or gathering information from other geometry in our scene, we want to put that all in one place and just should have a single cook. Or we could even cache that to disk and have a single point cloud representing everything that's going to happen. And from there, now we can go back to from time-dependent no to time-dependent yes. And at that point, it's really quick. All it has to do is isolate a point, like 5 points. So you have a very, very quick system for that. And lastly, we'll end up having these stick to the building. But let's recreate this part first. So let's go to our computers and let's work along, and we'll put this system together. So let's try to get that scene open. I'll help you guys. So at the top level of this geometry node, now keep in mind that a lot of these things I've built as either simple geometry nodes or subnetworks. And when you guys take this into the studio, you'll probably want to make your own digital assets out of these things. But for most things, I didn't make a digital asset out of it because I don't exactly know how you guys are going to want to use these workflows. and I wouldn't want to. When you make a digital asset, it's both powerful because you can copy it everywhere in the scene easily, but it's also restricting because then you'd have to open it, change it. Maybe it doesn't do everything you'd want. So these are a little more open, and that's how I tried to design the scene. So maybe you'd want half of this setup to make a digital asset out of, or maybe you'd want the whole setup, I don't know. But right now, I'm just using 2 spare parameters up at the top of this geometry node. For anyone who's, we're going to be doing this a lot, so to make a spare parameter, you right-click on any node, edit parameter interface, and one of the most common things that I'll do is I'll just go through and I'll hide the stuff that I don't need. So I'll just say, if I've got a geometry node that I'm never going to want to transform, I'll simply make that invisible. To see what's invisible, just do that. But okay. And I've got a spare parameter for tanks. Now this is an operator list, different than an operator path. An operator path, you can point to a single node, and it's got one of these little shortcut things. And that's really handy because it'll let you link right to that node, and you can click on it and it'll go there. Now, a lot of people don't know you can actually use stars in these as well. So if you have like 5 things that are different names at object level but the same name at geometry level, say you want to import all of the models in the scene, you would put a star here instead of that if they were named the same way. It'd import them all. For right now, it's just a single link to a building because it's colliding with the building a little later on, and it's got an operator list for the tanks. Now, it doesn't have a little picker because it's more than one, presumably. Now, the way to reference these, copy your parameter, you'd go down, you'd paste relative references. Another thing that might not be apparent is in an object merge. Now here I've made spare parameters on top. Okay, this is a chsop expression. So a chsop is really powerful because it actually is a native call in Houdini to find the nodes, and that's notably different than a string because a string could be anything, right? chsop will error out if it doesn't find nodes, or if it doesn't point to what we're talking about. So that's a good thing. So here I've chsopped to obj tank 1 and obj tank 2. Say we had 10 tanks in the scene, it wouldn't care. It would get them all. We could put a star or a wild card on there as well. Okay. So now, presuming these are all coming from the same digital asset or the same system or whatever we might encounter, I've got a similar prefix, and since these are digital assets, they're going to have the same subnetwork. So I'm going to append gun tip output to it. So going into tank, I'm just going to allow edit contents for right now. I've got a special geometry node in here, gun tip and output. So all that's doing is it's merging in a circle for where the actual gun tip is. So let's see. Tank gun. Oop. There we are. Okay. So here's the tank gun, and it's just got a separate circle in here. So I'm just putting that circle at the tip of the gun, and that's what we're getting this from. So in your studio situation, it might be a group on geometry. In this case, it's an object level transform, but it doesn't really matter. It could be anything we decide to call collectively. Okay. So just as a warm-up in this class, let's write a Python script to put this string onto both of these strings, or in this list. Okay. And if anytime we get stuck, it's all right here. Okay. So I'm going to make an object merge. edit parameter interface, and I'm going to give it a separator just because I like to keep things separate from each other, and then a operator list. We'll call this tanks. Then I'm going to do a string, and this is going to be what we're going to add on to it. So postfix or whatever we might designate that as. You can use your own names for these. It's really, we're just going to familiarize ourselves with the process. And then let's see, what else should we should probably do another either operator list, or we could just do a string. Let's see, which one did I do? I think I did a string. Let's try a string. Let's try refs. So this should be the final references. Okay. All right, so for tanks, I'm going to copy this guy onto here. Cool. All right. Now for this postfix, you can really gather anything. So you can play around with gathering different parts of the sub output. But for right now, I'm just going to go ahead and gather. I'm going to try to append that onto each of these things. And now for this, and this is going to be our first Python script. Who's worked with Python before? One person? All right, well, good. I'm really glad. I was a little worried this was going to be a little repetitive for people, but no, this is very useful stuff. And the reason why is because I've seen really nasty hacks for when a simple Python script could be used. And Invictus is a show that I did quite a bit of Python on for crowds, and using basic string splitting operations and string referencing operations is probably the most common thing that I do with Python in Houdini. So this is really useful. You won't want to do string cat operations or anything again. Now, that being said, Python is slow. In Houdini, if you do Python differently on 20,000 points, it's going to slow down your scene. So there's a time to use Python. In this case, maybe we're doing it on 100 points if we had 100 tanks in our scene. But that's no big deal for a fast computer or Houdini, whatever. If we did it on 10,000 points, that's different. We wouldn't want to do that. We'd want to come up with in-software like Vox stuff for that. But for Python is very appropriately used for something that's really hard to do and on a very small amount of things. So let's keep that in mind. Okay, so how do you do Python? Well, I'm going to put a keyframe here. Why is that? Well, all expressions in Houdini are stored on keyframes, and a lot of people don't know that, even if they've been using Houdini for years. You have to have a channel to have an expression on that channel. So I'm going to hit Alt left mouse and put a keyframe on my parameter here. Now, it didn't do anything yet. I don't really want a keyframe on there. That's really so I can switch it to Python. So I'm going to right click and go expression and change language to Python. Now it turns, in my computer at home, it turns purple. I think it's a slightly different UI here, color scheme, so it turned red, but whatever. We can tell that it's not green, and that's a good indication as to if it's Python. All right. So now, we really aren't going to be able to do much from here, especially in Python. In expressions, you might want to just write them all out as one list. In Python, you almost always want to edit the expression. So I'm going to right-click, expression, and edit expression, and that pops up a little dialog for us. So we're good to go from here. So now, this isn't like really hardcore digital asset stuff because we'd want to be a little bit more organized and clean. This is really just a get it done, do what we need to do, and get out Python script. So the first thing I'll do is say, hey, what is my own node? So I'll go myself as a variable. Myself equals who.node and a dot. a single dot in Houdini represents that node that you're using. So I've just made a call or a variable for the node that's being processed, which in this case is object merge 1. So if we wanted to test that out, I could go return myself dot path and nothing. Let's see. Oops. Equals. There we go. Okay. So myself.path, it gave us the full path to its own node. Okay. But we don't want that. We want to take the tanks parameter first. So to get the tanks parameter, I'll say tanks equals myself.eval parm. Now we could go myself.parm and list the parm there, .eval as well. This is just a shortcut for that. So it's one of the most common shortcuts, so we're going to use it. Eval parm. And the string that I picked would be tanks. You can do your own just so you know you've got it. Okay, your own name for this. So I can see tanks is the name because if I mouse over, I see that lowercase tanks right up there. Okay, so tanks is that. Now I'm going to return tanks to test that out. Okay, I've got that. Now we want to loop through this string and add this to them. So we need this first. Let's do dog first though. Okay, so let's say add string equals dog. Notice these quotes I'm putting on each time. Okay, that means it's a string. So now we could say return tanks plus add string. And that would put dog at the end of these two strings, but we actually want to loop through and put it at the end of each division. So for that, we're going to make a list out of this string. And for a list, we need something to separate it by, and a logical choice is a space. So we can say separate it by every time you encounter a space. Okay, so let's see. Tanks list equals tanks dot strip, and what that'll do is it'll remove any blank space at the either side of each the start or the end. So any blank stuff out here it'll remove, any blank stuff at the front it'll remove because we don't need that. So tanks dot strip, and now we're going to split it. Dot split. Now if we wanted to, we could split it by a string. So we could split it every time we get that, but we don't really want that. We just want a space. So the default is okay. The default will go to a space. Okay, so now we have tanks list. Okay, so now we'll do let's say new string. So we're going to create a new string from our tanks list. New string equals cat. Return new string. There we are. Okay. So for right now, we want new string to be blank because we're going to add to this string as we go. Okay, so that's blank. So now let's do a for loop. For tank in tanks list. See, this is no longer a string. It's actually a space or a separated list in Python. So for tank in tanks list, and every loop in Python or if statement in Python ends with one of these guys, colon. Okay, and then we have to do an indent. So for tank in tanks list, and this could be anything. This is just the variable we're using for each one. New string equals new string plus. Okay, so we want new string plus. Where's that? Add string. And add string has to be above it, otherwise it won't know what it is. So new string plus add string. and then, okay. Oh, new string equals new string plus tank plus add string. There we go. Okay, so now we've got, we're adding to this thing each time. Okay, so that's this new string thing. Then we're putting in tank, which in this case would be one of these, and then we're adding dog. Okay, so let's, instead of adding dog, we can add another eval param. So myself.eval_parm, and we want to add our postfix. So postfix. There we go. Now we just need a space in between this. So at the end of that, we're going to add that's a space in Python. There we go. So we've done that. That's a good little warm-up for us. So I probably wrote this differently than I wrote it in the example. Let's see how close I was. Expression, edit expression. So this is what I actually wrote when I was doing it at home. It's pretty much the same. Myself, objects, append, final string, adding. Okay, so it's pretty much the same thing with different words. All right, so let's go ahead and give that a shot, and I'll help you guys through it. All right, so we're just going to try to recreate that object merge. One thing I should mention, sorry, one more thing. To test it out, just copy this parameter and paste it into here to actually merge in your objects. Okay. Okay, good job on that, guys. All right. Our brains warmed up yet? Yeah. All right. Next step then. So yeah, this is one of those examples, and a few of you guys were wondering, okay, well, why is Python really necessary here? Can you do this with, like, have anyone ever used like string cat operation, like expression in Houdini, strcat? That's about all I ever do with strings in Houdini. It's just that one. Geez, maybe a replace in Houdini, very rarely. But anytime it gets more complicated than those simple operations, you quickly develop the need for Python. So while I'd recommend expressions and VOPs for like many points, 20,000 points, 100,000 points, with probably integers and floats and vectors, I don't recommend Python for that stuff, but I do recommend Python when you have, what's the most tank fires that could ever happen, like 1,000? That'd be a really intense scene, 1,000 blasts, and that'd really be fine for a computer, you know, and now we can do it all in one simple operation, right? So we don't have to really worry about some complicated string cat code that if someone else would pick up the scene and they'd look at that and see 20 string cats, you know, they'd be like, what is going on? Whereas Python, it's this kind of Python is easier. This is pretty easy to read. I've also seen Python gone the other way, where they could have done a network and instead they did 100 lines of Python, and I actually would prefer the network in that case to split things out in different nodes, and because that's more of a, I think, easier for Houdini guys to read. Okay, so on to the next step. So now we've got our tank gun tips merged in. Okay, and if I'll just view these points here, we see that, and home the screen, those are the gun tips at the end of each tank here. Okay, so they happen to be a single primitive. So notice we've got two primitives. They're just a circle, as we already showed. So each of these tanks has a parameter on it, fireframes. Okay, so it'd be nice to be able to store fireframes parameter on each primitive. That way we have one primitive, one string containing these frames, second primitive, second string containing these frames. If we had 100 tanks, it'd be the same thing. We'd have 100 primitives, we'd have a string on each primitive containing what frames that tank fired at, right? So how do we do that? Well, I remember when Python was first introduced in Houdini, and there was this thing called the Python SOP, and it's still in there, but I found that often it's easier just to use an attribute create for most things. And the reason for that is you can use local variables in an attribute create, and your Python expression will reference a local variable. What's a local variable? Okay, a local variable. I've got some swag up here. I've got mouse pads and posters. Okay, a local variable is a variable that is stored so you can easily say $, that it's a shortcut to accessing the data that's going through that node. Okay, so it's kind of like a shortcut. So in this TankFire system, I'm going to use the local variable for object name. And there's a really cool new thing that they've added in Houdini 12 or 12.5 or whatever. Create per primitive path. Actually, I think you can use, did I use per point path or per, okay, I used per primitive path. And that's really cool. You can do per point path too. And that's pretty awesome because what that did, I didn't reference it yet. Okay, it gave me this groovy object name attribute here. Pretty cool, huh? Okay, so that means if I merged in two characters, I would still have a string on each of those characters telling me where it came from, and that could be really useful down the road. Okay, so anyway, I'm going to enable my per primitive path, and I'm going to use this guy to gather those wireframe parameters. So I'll do an attribute create. Everyone's used that, I presume? Attribute create? Okay. So attribute create, and I'm going to say attrib wireframes. I always label every new attribute I add with attrib. That's just what I do. You guys are more than welcome to adhere to your own kind of conventions that you use. Okay, so here I'll do wireframes. This will be a primitive attribute because I don't really need it on each point. I don't know how many points I'm going to have. I just know that I get one primitive, so I'm going to put it on each primitive. And it will be a string. And you might say, well, why is it a string? Because I thought it was numbers. Well, it is numbers, but it's more than one number. So you have to represent it as a string. Okay? So here's a string. Okay, now I'm going to make a spare parameter on my attribute create for the object name. So string, obj name, obj. Okay, and then I think we need another string for the actual parameter we're going to get. And the parameter name in this case would be wireframe, I believe. Frames, I believe. Let's see what it is. Fire underscore frames is the parameter we want to grab. Okay. So I'll do harm name. Okay. Now we could hard code all this stuff in, but that wouldn't make a very good system, right? You might want to use this on your own systems, and it won't be called fireframes. It might be called lightning bolt frames or something. Okay, so object name. What is the object name? Well, it will be a string, $obj name. Okay, now if you evaluate this, it won't evaluate anything. Or it is, but we can't see it. Does anybody know why? Okay, well, the reason that we could see these and we can't see this is because it's different on each primitive. So it would evaluate to two things. So it just won't show you anything. But that's okay, because if I copy this guy to here, now my new, I can test like this. Oops. Ah. Where's my spreadsheet? There we go. Okay, so see, I copied and pasted it, and I can see, yes, this is actually copying this correctly. Blah, wireframes, or copying object name into my new attribute will get me that variable. Okay, so that's how to test it out, is to keep your spreadsheet open for this one. Test it out like that. Okay, and okay, so now our parameter name, that'll be wireframes. Let's test this out. There we go, wireframes. Okay, so Now we need a Python to do that. Okay, so let's see. Let's do the same thing we already did. So I'm going to go and set a keyframe and expression. Change language to Python. And let me take a quick look at what I already did just to make sure I'm consistent here. Okay. Here we are. Okay, myself, path, place. Yeah. Got it. Okay. Okay, so I'm going to go ahead and edit this expression. Okay, so once again, I'm going to say, okay, what's myself? Myself equals who.node, and pointing to myself. Return myself.path. There we go. Okay, so now we can see it showing up. We won't see it show up here, but, well, actually we do because it's only one result, but we can see it showing up in here. Okay. All right, now let's gather some parameters. So let's gather object name and gather param name. So let's see, obj name equals myself.eval parm, and that would be obj name. Is that right? Let's see. Yep. Okay. Return. Oops. Obj name. Notice I'm testing it each step of the way. I saw quite a few of you guys try to write the whole thing and then test, and of course there'd be a typo or something. Whenever I'm trying to write even a simple Python, and hopefully we keep them at simple because we're going to use Houdini's procedurals and for most stuff. But even just go through and test every step of the way, and you'll save yourself some trouble. Okay, so now I'm returning obj name. I've got that. Okay, so now parm name equals myself.eval parm. Parm underscore name. Return parm name. Cool, got that. Okay, so now we're deadly. Okay, so we have to go to object level to grab wireframes. So I'm going to do a string replace function because right now our obj name is 2 spaces down. Okay, so returning obj name, or let's say obref. Okay, I'm going to make a string called object reference and return that, and I'll show you guys what's going on there. Obj ref. Okay, so basically our parameter isn't on this node right here. Our parameter is on this node up here. So we need to actually get rid of this stuff down there. We gathered these primitives, but now we need to get rid of them, and we really just are focused on the object because that's where the parameter is. Okay, so I'm going to do obj name dot replace gun tip output with nothing. See how that worked? Okay. So I just removed the back stuff there. Now it's pretty easy. We're going to do a parameter call. So who.node obj ref, because that's a path to the node. Okay, this isn't a node yet, but now it is because I just did a who.node. Okay, dot parm name dot eval, and I'll say wireframes equals that. Okay, return wireframes. And we can test that out because up here, if we were to change this, remove that, get rid of one of those. Okay, so we almost have a fully working fire system. We're going to loop through it on the next step. For right now, let's try to gather our data into an attribute fireframes. Okay, questions on this before we go back to the desk?
Where's the who node object graph part again?
This guy?
Yeah, like why is it a
okay.
who node?
So the reason it's a who node, okay, so by default, objref, I'm getting this is a string. This is like an arbitrary string, and I'm replacing whatever with nothing. Okay, so that's just string data. So we can't do a parameter call on a string.
Okay.
So it has to be a who object saying this is a node in Houdini, and then we can do all these groovy object functions with it, like eval parm and parm eval and stuff like that. Okay, or you could do like path. So if I were to say objref dot path, it wouldn't do anything. It'll break this. See? But if I were to say who node objref dot path, now it's actually giving us the path to each of these values. Okay, so there's all these functions you can do on a node, and that's in the Python docs or the help or whatever. I'm not in the docs, and the reason for that is this isn't the Python course. These are just the most common things you'll use every week at a studio, or if you build a tool. You probably don't want to be a Python coder because that's a different job, but you're going to want to have these, and it'll really save you time. These basic who.node, who.evalparm, string split, string strip, string replace. As long as we have those, most of the rest of Python and Houdini we probably won't use every day, but those will really save us some time. So that's really why I wanted to start off the class with this. So cool. All right. So yeah. So we're gonna get myself, grab each object name from each primitive. Oh, one really important thing. If this is point, it'll break. Okay. We're dealing with primitives because that's where our attribute is stored. Okay. Get the parameter name we want to grab. Go ahead and grab it, and set and do your parm, and then evaluate it, and then we'll save that as an attribute on each one. So return fireframes. I'll leave this up just in case we get stuck. Okay, but yeah. Okay, so let's do that, and then we'll do the final part of it, which is a loop, for each loop, and I think that's pretty simple. Yep, that's pretty simple. And after that, we'll break for lunch. So I always like to go from an arbitrary input of who knows what to getting it on geometry as quickly and efficiently as possible. And once it's geometry, Houdini's built for geometry. So that's why we're going from taking an arbitrary input, which is this, then we're saving it on primitive, and then the final loop would save exactly what information we want in a format that we're all used to working with, which is points. So here, we've actually got a point for each fireframe. Okay, so what's this loop like? And okay, so I'm just going to demonstrate this for each loop, and I think it's pretty simple, so we can try it for 5 minutes after lunch if we want. But so how do we turn all these primitive attributes into that? Well, actually, how do we? I forgot what I did. Okay, so for each primitive, who's used the for each loop, by the way? Oh, most of you. Okay, that's surprising because a few years ago, TD stayed away from it. That must be getting quicker. Okay, so I'm going to do for each primitive, and that'll just loop through because we have one primitive per tank, right? Okay, so that would give us this guy. Okay, first primitive, and it's got just one set of fireframes on it. Okay. Now next, I'm gonna copy a single point. Have we used the add sub? Okay. One of the easiest and most simple things to do is to represent any arbitrary piece of data as point data. point clouds aren't just useful for positions and stuff and particles and things. They're also very, very useful just for arbitrary data. Houdini loves point clouds. I store paths on point clouds. I store path to geometry on disk, I store lots of things on point clouds. So here I'm making an arbitrary point, and I'm just setting it to the center of each primitive. So let me do that real quick. So add single point and the centroid expression. And the first string call would be dx, or you can just do a value of 0 there too. That'll work the same way. So dx, dy, and dz. Okay. And this should have placed our point in the center of our primitive. Okay. Next, I would copy this point the number of times for fire frames. We know we can't have more than one fire on a frame per tank, right? So it's safe to just copy it that amount of times. So I'll do a copy saw and set it to, oh, we don't know what this is. It could have like 4 fires, it could have 5 fires, it could have 0 fires, right? So for that, I'll do our last piece of Python for, I think, the day. And I'm just going to add a integer for the number. Let's say num. I wonder if that's already taken. No, it's fine. Okay. Set my keyframe. Change language to Python. Okay, and we would also need. I wonder if I had a node on there as well. Let me see. Ah, yes. Okay, I had a node for each of those. Okay. Okay. I know everyone's used the point expression, right? Did everybody use the prim expression? Not quite. Okay. It works the same way. And in case we're used to storing our data on points, this is probably a new experience for you guys storing significant data on primitives, but you'll find that especially if things like strings and things like that, like we have an arbitrary number of points, but we might just have one primitive, especially if you're talking about a particle system or something. So primitives are often a very efficient way to store data. So I'm going to go ahead and make a string up here. I'll call this frames. Okay, and we just want to use the prim expression. Now, I should have mentioned this earlier. Houdini likes these, at the far end of the keyboard, it likes these, I don't know what the proper name for them is, but it likes these kind of backticks. Whereas Python likes these kind of backticks. That can be really confusing, so watch out for that. But since we're in Houdini right now, we're not in Python, I'm going to use these backticks. Okay, so prim string. Okay, so that's the prim expression, and we wouldn't have we'd have a string attribute. Okay, so each, we only have one primitive, so it'd be primitive number 0, and the attribute we're trying to gather is fire frames, and it doesn't have a call because a string can only have one designation. Okay, and that didn't work. Let's see, why didn't it work? Fire underscore frames. Ah, yes. Got it. Thank you. So, so now we've got our frames, and okay, myself equals who.node. That okay. Myself dot eval parm frames. Now, so I'll call this frames string equals that. Okay, so this is probably the last useful string function I think we should all have in our Python tool set, is to count the number of things in a string. Okay, so the way we would do that is by turning it into a list first. We've already done this, so who wants to refresh me? How do we turn this into a list. Not with a for loop. No, an array is different than a list in Python. Yeah, we've already done this earlier in the day. How do we turn frame string, which is yes, split. Good. Okay, so the split function turns your string into a separated list, right? So let's say frames list equals frames string dot string dot split. Okay. All right, so that'll turn it into a list. Now that won't evaluate because this is an integer, so we won't see anything here. So we just have to go on faith for now. How do we get the length of frames list? Well, we'll say num equals frames list len and return. There we go. So len gets the number of items in the list. Okay, so that's easy. Now we just use that to copy. Like that. So we'd make 3 copies of these points. We now have 3 points, and we would just have to do something final to get each attribute on that, right? So let me take a look at what I did over here. Okay, so another attribute. I'm sharing a few of the parameters, but here I have a reference for the point number. Let's see what's going on. Okay. That's easy enough. Okay. Let's see if I can wing it. Alright. Attribute create. So we have 3 points. We just, they don't have any information on them, right? They have a position to the centroid and that's it. So we want to get the first frame on the first point, the second frame on the second point, and the third frame on the third point. Okay. So we'll call this fire frame. Not fire frames, it's just a single. It could be a float or an integer. I'm going to put it to an integer. And we would need, once again, a local variable. So I'm going to give it a local variable for the point number. You can do that in Python directly, but it's just easiest, I think, to have all of the variables you're going to need as spare parameters up at the top. And that way there's no confusion. There's no who.geometry.point.whatever. You can just have everything laid out with HScript. And because that's really what HScript is good at, is referencing the easy stuff, right? So, okay, integer. I'll call this point. And this will be $PT for the current point number. Okay, so I'll use point in my expression, in my Python expression. Okay, also we of course want fireframes, and we'll just get what we already got here. So I'll go ahead and steal this. Could reference it too if you wanted to. I think that's all we need. Okay. Keyframe. And switch to Python. Edit expression. Okay. Let's see. So we have fireframes equals myself eval fire frames. We have a point number equals myself dot eval parm. There we are. So now we want to get a list once again, and we're just going to access that number in the list. So frames list equals fire frames dot strip dot split. Okay. Now my frame, or I could say fire frame, equals frames list. Now the way to index a list would be like this. These two little brackets here. So we'll just put the variable we have for point in there. See if that worked. No, it didn't work. Okay, what did I mess up? Fire frames. Frames list is fire frames. Split. Point measure. Anybody see anything weird? Frames list. Well, let's return 10 just to make sure it's working. Okay, that's working. Return PT, make sure that's working. Oh, I know why it didn't work. Okay, so this actually isn't an integer. We'd want, this is still a string, and you can't return a string as an integer. Okay, so on our frames list, we need one more little expression, and that's the int. It'll turn a string that says 10 into the number 10. Okay. Return fire frame. There we go. Okay, so that's inside of a for loop that's doing each primitive. So the result of that for each loop should be however many points are actually firing. And we'll use this through the rest of all of our systems to do all of this groovy tank fire and everything, fire destruction and all that. So now we've got an organized set of points, 5 points in total, that does that. And I believe I'm time shifting. Nope, not time shifting yet. But we'll do this part. We won't do this part, but we'll do the time shift part after lunch. So, cool. Okay, so that's a lot of Python. I'm sure everyone's brain hurts and they're like, okay, God, give me an espresso now. So let's take a lunch break. That's all the Python we're going to do for the rest of the MasterClass. So be relieved, but that's I think if you know these basic functions, you'll be able to build your own tools a lot easier. String split, string replace, length of a string array, or string list rather, getting nodes, getting parameters. That's really all I ever do on a weekly basis when building tools in Houdini is those Python calls. So hopefully we have this scene to take with us. We'll always be able to do those things now, and your tool creation should go a lot smoother, I hope. Geometry to store important information to be used in the scene later. So that would be, let's pick up about here where we have an attribute create for an ID, and what this guy did was he just made a bunch of points, 5 points at the centroids of their associated primitives, and also we should note that they have normals. So the normal would be the direction that the gun was facing, and we just get that by the fact that their primitives had normals as well. How did I put that on there? Oh yeah, I'm copying the normal here. Okay, so from the primitive, I'm copying, along with the getting to copy frame and things like that, I'm copying the normal. Has everybody seen an attribute copy? Okay, yeah, attribute copy is actually really awesome. Before I really discovered it, I was using something like points, and I would put an expression in the point to gather like something off a primitive. But if you can get away with using an optimized tool like attribute copy, it's much quicker. It'll make your systems run a little bit faster copying attributes from place to place. So all I'm doing here is I'm copying the normal. So we have the appropriate amount of fireframes on these points and the appropriate amount of fireframes on these points, and they are moving as the tanks move. So what I want to, the last part of this system that I want to convey is something that not a lot of people are comfortable doing that will really improve your setups, and that's looping through time. Who's done like a loop through time or something like that, like calculations on a full frame range basis before? Okay, a little bit maybe? Okay, so you can do that in chops. The problem with doing it in chops is that you really have a lot of things to cache out, and you might only want something really specific. Like if you have, you know, only 5 points, we probably wouldn't want a giant animation range for all those 5 points. You probably just want to do a very specific thing. So in SOPs, I really like to cache out through the full time range with a for each loop. So I demoed the for each up here, but let's actually get in and use a for each and loop through time. So the idea would be that we have these fireframes. We have, they're moving according to the tanks. And we know which frame they're going to fire on. We know that the fire frame for the first point is 25, the second point is 45, so these things aren't going to change. But we really just want to bake in the positions of these things in time. Right now, our system, as efficient as it is time dependent, yes. And there's really no reason for it to be, because we know when something happens. So now we just want to bake it out and have time dependent no. So I'm doing a time shift. Everyone's familiar with time shift SOP? Okay, time shift SOP basically makes your scene cook. Whatever's going into it, it goes to that point in time and cooks your scene, your input in that point in time. So it's very powerful. I remember when it came out in Houdini 9, I believe, and it was just like, wow, that's awesome. I needed that for so long. So here I'm locking these frames to the start with an F start, the local variable for the start of your time bar. Okay, so now it's not time dependent anymore. We can scrub all day. It's not going to affect our performance. And with this for each loop, we're going to do our time loop. So here's where we'll pick up. So in a new for each, call this my time loop or something. Okay, I'm going to plug my non-time dependent part into the first input, and it has everything we need. It has that fire frame on it, and we're going to use a time shift to gather information from the second input. Okay, so boom, there we go. And let me review what I did here. Yep, that's pretty straightforward. Okay, point. All right. So in the time shift loop, we want to apply a separate process to each point. So I'm going to say each primitive slash point, and then by default it defaults to primitive. So I'm going to turn on apply to points to make it apply operation to each point. And we only have 5 points, so it's very fast. Okay, we'll go in here. We should see our first point. Call this each. And on this first point, we have the fire frame. In this case, frame 70. So in the second input, time shift, I'm going to gather frame 70 so I can get its position and normal. So for that, I'll use a point expression. Point each, point number 0 because there's only 1 point. String attribute would be fire frame, and the index would be 0 because it's a float. All right, so that's going to shift the second input to frame 70. And anything else we need to do in here? We'd probably still want an attribute on that to designate the fire frame. So let's try out the attribute copy for that. So I'm going to copy from to fire frame from this attribute. or from this, I'm going to copy fireframe from my each. Say copy fireframe. We don't want color, we want other attribute, fireframe. And that should get fireframe of 70 onto our second input. There we are. There we are. Okay, cool. Oh, and one more thing I should mention. We should delete everything but this point. So we'll use a delete stop to get the ID and isolate by ID. So before you go into a loop like this, you should always kind of, if you're going to do branching from different inputs, we should set an attribute to designate what point that is, because once it goes into a for each loop, each point, it's like whatever it's processing, it doesn't really know what to gather from the second input. So I'm just going to make sure that whatever goes into my second input is the same ID as what goes into the first input. So before I do that, I'm going to say ISO by ID. Points, non-selected, expression. So ID equals point each 0 ID 0. And that should just give us whatever point we're actually processing. Okay. So now we've successfully baked all of these fireframes into their appropriate times. All right, so we can visualize this, and we can, as we scrub through the timeline, our guns will be doing that. See, that point 0 is a little bit odd to me, actually. This guy looks like it's working fine. Yeah, that's working fine. Oh, point 0 happens on the very soon. It happens right about here. And then the gun switches over and fires there. But I encourage you to play around with the frames and see. So that's the next exercise, to bake in time our frame age. And now it's not time dependent anymore. We can apply operations to it all day, and the only thing we're going to have to worry about cooking is this optimized system full of 5 points, or however many points you have in firing frames. So let's give that a shot. I'll be around to help, and after that we'll get into some particles. All right. Complete separation, all the tools you guys make between when and how and where, represent that as simply as possible. Represent it as point clouds, represent it with directions like normals. If something happens on a certain frame, represent that as an attribute on a point cloud. So everything here is non-time dependent. Time dependent, no. And you can base your whole system off it. It's like having an Excel spreadsheet in your Houdini from then on. And yeah, we're making it out of Houdini nodes, but that's why, one of the reasons why Houdini is so cool is because we can do this in software without writing. I know that probably seemed like a lot of script, but compared to the scripts that most scripters write for the stuff, that wasn't script. That was just like a few expressions and referencing some attributes and stuff. We were trying to avoid the giant scripts that are custom made for a setup. Like, you can use this setup really to gather anything. Maybe we're gathering firing on tanks here, but you can use it for, like, I use the same system on Ender's Game to do tracer fire. It's the same thing. They said, oh, we want it to happen on this frame. I'm like, okay. I didn't have to keyframe or anything. I just put it in, and we had an unlimited amount of ships buzzing around too, so it became really handy not to have to do a custom setup for each spaceship. So, all right. So moving on. Now we've racked our brains and come up with this groovy spreadsheet in Houdini that's non-time dependent and has all the information we want. We have fireframe, we have position, and we have normal. Now let's do stuff with it. Let's base all the rest of our systems on this data. So the first thing we're going to do is make it stick to something. We're going to make it stick to the building so that we know where to fracture our building. Okay, so how many people have like fractured a building or something like similar before? Okay, you guys give me like an overview of the kinds of techniques you've done. Did you fracture it on every frame? Did you fracture it all at once? What kind of techniques did you guys use? Who's brave?
Refracture and then assuming like those pieces.
Yeah. Okay. How did you know where to fracture it?
Didn't really, just kind of art directed.
Okay. Okay. See, with this system, we're going to know exactly where to fracture it. See, so we have our points that we know where we're going to fire. If the animators redo it, for instance, say we're not the ones animating it, say some other people animate it. We don't have to, oh, I fractured that part of the building, but now they want me to break this other part of the building. We don't have to go back. Okay, so these points enable us to have one system that'll automatically adapt to change. So now I know this seems a little redundant, but since this is time-dependent no, here, pretend this doesn't exist. Pretend this is all just one thing now. Now I'm making it time-dependent again, and I'm isolating the points by the current frame, and that just makes sense for particles, right? So here, if it's on that frame, it's gonna fire on that frame. And the way I'm doing that is with the delete SOP. If $F for frame is equal to $fire frame, the attribute we put on there, then keep it. Otherwise, don't keep it. Okay. This is markedly different than, now this is for the mouse pad guys. All right. What is the difference between okay, so these are all my fire frames. Okay, so this is my time-dependent system that has all these frames on it, right? Okay, so what's stopping me? Why wouldn't it be good to plug this in here and just do the same thing? See, I've got the same result, but why is that loop we just did better than this? Why did we just do that? Anybody know?
Just less processing?
Yeah, that's the thing, is that to base other systems off of this, if it says time dependent yes, what that means is it's going to redo everything up to that. And also, if something we're feeding it in is downstream, isn't time dependent, like the fracture of a wall, we don't want to have to refracture it on every single frame. Okay, we don't want to have to recompute our systems. We just don't want extra needed baggage. So that's why whenever I'm building digital assets or systems, I'm always trying to get as much data as possible stored in a single cook and go from there. So from now on, I really hope you guys store your attributes on frame as store when things happen on attributes. And that's really kind of the power of Houdini that people never really tap into, and they should, because it's really great that way. So I'm taking my non-time dependent system, plugging it into a delete SOP and getting the right stuff out of it. In this case, the current frame. Now we're going to merge in the building, and we can put anything here. You guys can try out different shapes if you want, but for right now, let's do the example, and we'll play around with it once we build it. So so here's the particle with its normal, or the point with its normal at the right time. Here's the building. And let's make it stick. So here's where, in the source pop, in a new particle network, let's just do this from scratch. Okay. We want to first determine how fast this thing is going to shoot. Okay. So, you know, if we want a velocity of really, really fast or really, really slow, this would be the place to put it. So here, I'm going to put in 100. I found it was just pretty fast. Okay. Now, let's source these things. So we'll do points ordered, right? Because we just have one point that we want to do it on. we want the first context geometry, meaning plugged into the first input. For birth, we want impulse activation is on. We can turn off the constant activation because we don't want a continuous stream of stuff. All right, and the impulse birth rate. Now, if we had more than one point, which could happen if we had two tanks, we'd want the NPT, right? Who can tell me what that is? Yep. Okay, so that's a local variable in pops to determine the number of points coming on the input of a source pop. So, $NPT. That's just a default thing. We didn't have to do anything special there. If we want to keep our attribute variables, I'm just going to check this. Create local variables. And that should be it. Okay, so we should see some particles shooting out of here now. Boom, boom, boom. There we go. Got it. Okay. Nothing special yet. All right, so now let's make it collide. So I'll add a collision pop. You don't have to have this template flag on. I'm going to keep this guy. So I collide with wall. Okay, so for this I'll use the second context geometry. It's not deforming geometry, it's static geometry. And behavior will be stick on collision. Who can tell me the difference between sticking and stopping in pops?
Stays active?
Yeah, so when a particle is stopped, it's no longer computing anything. Okay, so it's not going to update its position, it's not going to update its normals or velocities or anything like that. It's angular, like say it had spin on it. It would stop spinning. Now with stick, it will actually stick on that barycenter of the polygon. So there's a way to compute where it is in a polygon, and that's the barycenter. And if you had deforming geometry, it would try to keep that. It would stick on it. So I found stick is probably better for this example. Okay, so we'll do stick on collision. And now we want to save this out as a variable, as an attribute. So in pops, there's an attribute create too, but since it's so old, they don't call it attribute create like they do in SOPs. They just call it attribute. So it's kind of like, imagine a point SOP and an attribute create as one thing, and then take away all the presets. That's the attribute pop. Okay, so attribute pop. All right. So now I'm going to go is stuck. That'll be my variable, is stuck. And it'll be an integer attribute. And I'll write the value, but we don't know that yet until we add a state pop. Now, looking in the help, this will tell us that this adds certain local variables for us. And we could do it by default, but pstate's a little tricky because it's actually a bit lookup. Keep in mind, pops was built in like the early 90s. Or actually, I think it was before then even. I don't exactly know. I know it was Flight of the Navigator, whenever that was, okay? So they didn't want to waste memory or resources, so they made pstate as a it says collectively as bits. Okay, so it means it has like 16 possible values that it could be. So this will actually put the local variables on. So here I'm going to put on the attribute stuck if it's stuck. Okay, so it'll instead of like doing a bitwise operation, it'll just give us 1 if it's stuck and 0 if it's not stuck. Okay. And so we can feed that into our attribute is stuck, and then we can just do the value stuck. Okay. And that's our system. That's our first pop system. It doesn't have a local variable with it, so that's where who has had to try to type in a variable and have it go red, not because it didn't have one on it, but because it didn't have a local variable associated with it. I'm sure we've all probably run into that situation, right? So whenever that happens, I'm just going to refresh it. So I would always call this like refresh is stuck or attrib is stuck or something. Okay, and all we're doing here is we're taking that variable and we're just reassigning our is stuck right here. Okay, so I just turned off write values. Okay. Now we're just going to isolate the particle if it's stuck. Okay, so only 3 particles got stuck to the building. Okay. All right, let's see if we can put that together. After that, we're going to fracture the building using these points. Okay, so wall destruction system. Now this will be in a different node. Okay, so we ended the tank fire system with we're outputting is stuck. Okay, now this is time dependent, but basically what we'll get is we'll only get the points that are stuck, and they'll just appear as they're stuck. Okay, so we'll use that to break our wall apart. So in the building destruction system, that's we're moving on to a new node here. Building destruction system. I'm merging the output stick points and also the building model of the building. Okay. All right. So first, let's take a look at these stuck points. So obviously, I was preaching about not having things time dependent, and now our stuck points are horribly time dependent, right? And even worse, in pops you can't go backwards. So we want to eliminate that as soon as possible. So for that, we should be familiar with this technique by now. We're going to use for each SOP. Now this is probably we actually did a more tricky way previously than we'll do now. This is actually really straightforward. Bacon time. So for this for each, as we're following along with this system, I'll probably just divide it into a few key parts as we go back and forth for the rest of the class today. Go ahead and just try to make the nodes we see, or you can copy and paste nodes if you don't want to, like say we all know how to do an object merge. Just go ahead and copy it. Okay, so you don't have to waste time like that. But the important things, the systems that we're unfamiliar with, we'll go ahead and build those. Okay, so one of them is bacon time here. So for this guy, this is a for each loop, and we're going to cache out in a non-time dependent, not class form, for each loop. This is something common that I do quite a bit. I go for each number, and this functions just as a for loop in programming at this point. So I'm going to go from the start frame to the end frame. Fn. Okay, those are the local variables for that. And if I just let it go, what I would get is nothing really. It's not doing anything yet. So going inside, I probably want to do another time shift. Okay. So you actually don't need an each. I'm going to do a time shift, and for the frame number, I'm just going to copy and paste where the each SOP is getting its value from. In this case, it's the stamp expression. Okay, it's stamping the for value up here. So instead of $F, I'm going to put that stamp expression in there. Don't need my each anymore. I'm going to call this F. Okay. Now, what this will do is it baked out all of our points in time. So now it's not time dependent anymore. The problem is that we've got a lot of points that we don't need. Let me check to see real quick. That is actually a little more tricky. Ooh, I don't know if we're ready for that one. I'm going to demo this one, okay, guys? We're not going to do this one. Okay, so. Okay, so here's something we always want to do with the time-dependent loop. So we're looping through this. Okay. And I'm going to print my progress. So with the script SOP, I'm going to print what I'm doing. So let's say print eval at frame who.eval arm. And here I'm going to do a reference to the $F frame number, that parameter. And what I should get here is I should get this Houdini console pop-up, and it'll be frame 0 because right now it's not evaluating too much. I'll call this guy print progress. Okay. Okay, so now we've looped through the whole time range. That's something that I just like to do because if it's longer than a second, I want to know that it's still working and stuff. In Linux, it's a little easier because it shows up in your console, not your Windows, but make do. Okay, so this basically means that it's looping through our time and gathering all of our points. So we want to be a little more tricky than that. We still only want 3 points, but we want the first occurrence of that point. Okay, and our frame attribute doesn't do us any good anymore either because that's the frame it was fired at. It's not the frame it hit the thing at, right? So we need a new attribute for that. Okay. Got it. Okay. So if this doesn't make sense as I go through it, I'll answer any questions, of course, but the best thing to do is probably just to kind of take in the process, and then next time the opportunity presents itself, whether you need a feedback loop or something like that, then just go over the system, study it a few times, tinker with it, and see if you get the vibe. So in this case, what we're going to do is we're going to do a feedback loop in a for each loop. Feedback is different than merge. Merge, when this guy's checked, it will take everything that it loops through and it'll save a copy and it'll compound itself for each copy. Feedback, on the other hand, takes wherever the each is. So I'm going to do my new for each just because it gets initialized with an each stop in it. Sorry. Control C. Control V. Okay. Okay, so this is our each right here. Okay. So when this merge result is on, then this little feedback guy on the each will be off. I'm going to turn this guy off, merge results. What that actually means is it's feedback loop now. It means that each result is going to add to the previous result in its geometry calculations. So we can actually call this feedback. Okay, because now this little feedback box is checked. Okay, merge results is off, feedback, it means it's a feedback loop now. Okay, so pretty much what I want to do is I want to test to see if the point exists yet. Okay, and I'm also going to have an attribute on here to record the current frame. So attribute create, and I'll call this impact frame. So the first frame it appears, it's going to be the frame that it impacts the building at, right? So I'm going to do integer, and I'll just minimize that guy. And we'll copy and paste a relative reference from the frame parameter here to this. Anybody have an idea why the $F wouldn't work here? Okay, it's because we're actually not changing the time. So we're still on frame 22. Even though it loops through the whole time range, there's the $sign for $F, local variable would always evaluate to 22. Okay, so that's why I'm copying and pasting the parameter that I'm setting here for this frame into here. So attribute impact frame, copying that, I'll call this packed frame. Okay. Now, notice that I have this branching out on the other direction from the each. So we want to do a test. We want to see if it exists or not. So I'm going to give it an attribute. So attribute create, I'll call it exists. Exist 0. Exist. And for this guy, I'm going to use op digits. Anybody seen that before? Yeah, okay. It's a good way of making sure you don't spend an hour saying, why isn't it working? And they're both set to 0. Okay, so this is exist 0, meaning it doesn't exist yet. It should be above the feedback loop. And then I'm going to make exist 1. And this is everything new that's being read in. Okay. Now, in a point SOP, I can compare these things. Each particle has a unique ID. So what I'm going to do is I'm going to check to see if the ID exists or not. So the way to do that is to match by attribute, and in this case, matching by the attribute ID. So, exist 2. Okay, so if it's present in the second input, then exist 2 will be set to 1. If it's not present, then exist will remain what it is in the first input. Okay, and let me see what's next. Okay, tag frame 0, 1. This is 2. Okay, yeah, it's a bit tricky. Okay. And actually, we don't need anything in the first input. It's simply recording what's already been done. It's feedback. Okay, let's see. Yeah, even I'm lost. Frame, print progress. This is 0. Oh, okay. Now we're talking. Okay. So, things get read in by time. They're set to exist 0. Then the previous result gets put in from here, and if they already exist, they'll be set to exist 1. And that'll be the test. This will be exist test. Okay. There we go. Each frame, previous iteration of the loop, right in here. So now, we would delete what already exists. So if it was set to 1, we would delete it. Delete points, delete selected. So I would call this kill exist. Now, if it didn't exist, if it's the first time it ever gotten used, then we'd want to keep it. So we would simply merge it with the previous results. So for that, let's see, what did I do over here? Yeah. We'd kill it if it already exists, otherwise it would be merged in. So this feedback would actually be the result of all this, and it would go into here. So it's the result of whatever the display flag is at. pretty much it. Let's see if it works. 3 points. Let's see if they have, okay, so yeah, they have the first frame that they got stuck at. I know that probably didn't make sense. I'm going to go over one more time. Okay, so first iteration of the loop. Frame f start to fn. That's what I used here, right? Yeah, okay. Okay, so first iteration of loop, nothing happens. We have a blank add stop. Okay, there's nothing there. And this is what gets fed in the first time. Then it'll say, yes, I do exist, even though there's nothing there. It'll get tested of what's coming into the second input. What's coming into the second input would be frame start. Impact frame would be added. Progress would get printed. And exist 0. Okay. Meaning it doesn't yet exist. It would make it through this test because if new stuff is coming in here, it won't get killed. Exist would be 0. Then it would get merged in. Now, the second time around, the second iteration, all of this result would come and start back up here. So that means that now we might have a point on that. The point would go through, yes, I exist. It would actually tell the same point in this thread, hey, I already exist. So the second time around, it would get killed. Okay. So, anybody get that? Anybody have any questions? Anything? I know I probably lost everybody there, but this is about as complicated of a for each scenario as I've encountered. Generally, people are comfortable with merge results, but they're not comfortable with feedback. So feedback is taking the previous result of the loop and doing something to it, and that almost always involves a test and then a merge. So you're kind of merging results on top of itself, testing them to see if they're valid or not. It really gets into more of a visual programming at this point. So what this for each loop does is basically takes in however many points and uses their ID to determine if it's the first time they've seen the ID, and if it is, they'll keep it. If it's not the first time they've seen the ID, it'll discard it after that. And that way we can gather the frame it impacts at and the correct position that it impacts at and all of those things. So I know that was probably too much, but come back to it. If you take the time and study it over tonight, or who knows, then and you have any remaining questions, I'll be more than happy to try to explain it in more detail. But yeah, that's a hard one. Okay. All right. So anyway, bacon time. All right, so don't worry about that. Okay. So now onto the building. We've got our points. We know what frame they happen at, and they are not time dependent. They're just stuck there. Okay. And we've got our building. Okay. So there's our points. There's our building. I'm going to give this an attribute, primitive number. And the reason I'm giving it an attribute is to, I want to test to make sure that I'm actually going to need this primitive. Okay. There's PR. Okay. Now I'm going to facet it, and that's just a good thing to do so that we can actually separate out the pieces. Here I'm cusping the polygons. I don't want to, I want to have the normals where they should go and have the polygons as easily separatable pieces. Okay, so now I'm going to take prnum and attribute promote that to a point. Who's used the attribute promote before? Few of you guys. Okay, half the class. Attribute promote is one of those nodes that hides in the software, and all these complicated things that, oh my god, how do I do that? Attribute promote is not just for compatibility. So often you'll run into a situation where a primitive number needs to be instead a point number, or primitive attribute needs to be a point attribute needs to be a primitive attribute. Okay, so that's an obvious use for the attribute node, is to get everything compatible. But that's really not the power of it. The power of it is that it's really, really useful for doing all of these other functions. It's actually a way of doing averaging and testing to see which one occurs the most, and all these really, really useful things. It does it blazing fast, and it'll save lots of loops and lots of other things if you use it. For right now, I'm just using it to convert PRNum to point, and the reason is because I'm going to gather a point attribute. Okay, scatter. We couldn't do that if the PRNum was a primitive attribute. See, now that it's a point attribute, when I scattered it, I've got PRNum on here, on my points, PRNum. Okay, so this is a really good way to test with now. We couldn't really test it in this state. We can test it in this state though. Okay. Now, who has worked with the awesome new point cloud features of VOPs? A little bit, one person, two people, maybe a little. Okay, so consider this digital asset a very useful thing. I've made it in the destruction tool set. Okay, it's in our OTLs folder. And let me just give a quick explanation of this. So what this will do, and most studios have something similar to this, is it takes in an input from the first input, and it takes an input from the second input, and it uses these point cloud features to open up the second point cloud in VOPs as, see, it's opening it up in the using the op syntax. So it's like an external file, but being held in memory. And then it's using the point cloud lookup, or point cloud open, and then it's getting it's referencing the point cloud based on the same way that Mantra lighting works. Okay, so it's using the same technology. Basically, it's a very, very, very fast way of accessing data that would normally be really, really slow. So the slow way to do this, which if you had a lot of points in here could take up to like 10 minutes or 20 minutes, would be that I could use some kind of an attribute create, and like say I could give an attribute called near point, and I could use the near point expression. So scat tx ty tz. Okay, and I think that would give me the nearest point for, okay, for this node. But the problem with that is it has to go through and do that expression new each time. So for this point, it has to look at that whole piece of data and say, is this point the nearest? No. 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 Okay. And that's really inefficient for, say you have 10,000 points in the first input and 100,000 points in the second input. You start doing that, and your systems will slow to a halt if you have to use extensive use of that. And I used to do it that way. I used to use the near points a lot and find stuff like that. You don't have to do that with this new stuff. So I've made a digital asset. We have a search radius, so it'll only access things within that radius of the position. We can either gather the distance or the nearest point as a near point attribute. Okay, and this thing's blazing fast. So, and if you're curious about how to make one of your own, just look in here, and this is how. Okay, so from that we're gathering the nearest point. We're gathering what's the nearest point of scatter to our particle impacts. Okay. And we should have the same result as before. Okay. Okay. Now, how do we use that information? Well, for that, we can extract some useful data. All right, so we can extract, for instance, the normal. All of these things have our nice faceted normals on here, like that. So when you use that in VOPs to get the normal, we would actually use the near point to access the second input. So this is probably one we're gonna want to do at desk. This is a really useful thing anytime you want to do it in VOPs. So basically in VOPs, we have our attribute, and we have our arbitrary points in the second input. What we would do is we'd import this attribute for the nearest point. Near point in point 0, in op index 0. Okay, so import. Now I'm going to use another import attribute and use that for the point number of op index 1. Okay, so we could gather any attribute. In this case, we're going to gather the normal from index 1, or yeah, this guy. Second input. And we would set that to the normal. Okay. Previously it was the normal of the particle impact. Now we're gathering the normal from our point cloud. Okay, so anytime you want to gather an attribute, I would, from two arbitrary things by distance, I'd recommend not attribute transfer, not near point lookup and expression. I recommend a VOPS point cloud import system, and then using that near point to actually find the exact nearest point. That's blazing fast, and it'll make your systems work really good. Okay, so so we've got the normal, and I'm designating that as an attribute called hit normal. So there's that. Okay, now the next thing is we're going to test to see which things were hit. So I've got a circle, dividing the circle, and scattering points on it. Okay, now using this, we want to move it back from the impact using this normal. So here, I've got a system that will, a VOPS SOP, that'll simply take this and move it along that normal backwards. Okay, and I'll show how we did that in a little bit. Copying the circles onto that, and then ringing them onto the surface of the building. Okay. Now, who's used the ray SOP before? Cool. Okay, so ray SOP is awesome, and in later versions of Houdini, we can set the direction any direction we want. It defaults to normals though. Okay. Now, there's also this little feature about that people aren't as familiar with. Create point group. Now for that, I'm going to gather a ray group, and that easily allows me to kill the things that didn't intersect. So here we're just going to kill the points that didn't hit the building, okay, by deleting by ray hit group. The next thing we're going to do is gather the PR num that we set up here. Okay. All right. So now, taking our building, we've got points, we've got a bricker building, better for fracturing. Now I've isolated everything that wasn't hit, every PR num that wasn't hit. So here in this thing we have all of these points that have a PR num on them. We only want to use those PR nums. So you call this each actually. Okay. ISO by PR num. So all this is doing is it's saying my PR num equals what's on the point. Okay. So it's looping through what's in the first input for each attribute value, in this case PRNum, and it's gathering what's going into it in the second input. Like that. Alright, so who's used connectivity? Cool. Alright, so we're just testing to see what's connected, what's not. So we're going to get probably one big piece here and all these little pieces. Now this subnetwork, we're going to test to see if it's big or not. So we don't really want to fracture these little pieces out here. So for this, we're going to make use of that attribute promote that I was talking about earlier. So in this case, what it's doing here is we can selectively get rid of everything that's below a certain size. Okay, now that's useful anytime you want to fracture something. It's taking out the junk. So using this, okay, how do we set up a system like that? Well, we'd want basically going into it, each PRNum, we want to test to see if this primitive is worthy. And I know already that this primitive is not worthy. It's one of the small ones. How do we get the area? Well, here's the area of all the polygons. But the problem here is that we've got 4 polygons. This polygon has an area, this polygon has an area, this polygon has an area, this polygon has an area. Okay? So if I look at my area spreadsheet here, it saved the area, but that's kind of like all these things have arbitrary number of polygons. How do I get the sum of all of that area to see what's bigger than what? Okay, so any ideas? Alright, so it's that attribute promote. I'm going to take my area attribute. The original class is primitive. Now the only type of attribute that's global is a detail attribute. Okay, so let's just do a little bit of testing with this. Here's my spreadsheet. Where's my spreadsheet? There it is. Okay. So all of these areas would actually get put from a primitive to a detail attribute. So points, vertices, primitives, detail. Okay? So all of this area, if I were to do first match, then I would get the area of the first primitive. If I were to do average, or minimum, okay, that's the smallest polygon. Okay? Maximum, that's the biggest polygon. All this stuff is really useful. In this case, what we want is we want the sum. That sums up the area of everything in this for each loop right here. Okay. So we've summed it. Now I'm going to convert it back from a detail back to a primitive. Okay? And that way I can access it more easily, because we don't want it as a detail attribute, because when it gets out of the loop, then it would have conflicting detail attributes for all these things. So it would just go with the last detail attribute it found. So yeah, we're going to turn it back to a primitive before it gets out of the loop. Okay? In this case, we'll do first match, and I'm changing the name to sum area and then refreshing sum area. So what that did is it actually gave us each connectivity has its own unique area. You can do area. See, there's whatever polygon this was. Here's whatever polygon this was, group that was, all these other groups. Okay, and then when I do my kill, I can read from this spare parameter up here, what do I want the minimum area to be? Now we can just test, is some area less than the minimum? If it is, then delete it. If it's not, then keep it. Okay, so this kind of a system is useful anytime you want to just test all these connectivities or groups for their area. And so loop through this and give this a copy paste. Alright. Alright, so there. So now this is what we'd want to fracture. Would be this. here I'm going to create my fracture geometry. Okay, so we've got, I think I'm pretty much just extruding it here. Let's see. Okay, so fusing all of the, any like faceted stuff together, extruding. And anytime you do a negative extrusion, you probably want to reverse your polygon normals before a fracture. Okay, so negative extrusion, I'm extruding backwards from the building, which just makes sense. I don't want to extrude into the building, I want to extrude back. That unfortunately left my polygons backwards. See, they're actually jutting into the building. So a reverse SOP will clean that up. So if you know your extrude is going to be negative, go ahead and drop down a reverse after that. Okay, there's that. From here, okay, this is a circle that has points scattered on it. I did, and then once again, all these systems, if you feel the need, go ahead and copy and paste, dissect later. But let me just give a brief overview of this kind of a technique. So here's a circle, scattering on the circle. Okay, no big deal. We see lots of points, we see a circle, but generally with any kind of a hole in something, a crack in something, we want more points to be where we want the main fracture, and we want less points as it goes out from the fracture. Okay, so in this case what I'm doing is I'm going to compute the distance from the center. Alright, so the distance from center, that's really easy. That's just a position, a length VOP. Okay, so the position, if it was like, right now we're at origin, by the way. Okay, so we haven't copied it yet, so it's at origin. So if it's out here, it's going to have a bigger length than in here, closer to 0, 0, 0. So length of the P, and then I'm saving that, I'm adding an attribute, dist. Okay. Now, once again, with attribute promote, I'm going to gather the maximum distance, but this time I'm not going to delete the original attribute. So what I had was P and dist here. Now I have P, dist, and max dist as a detail attribute. Rather, here, max dist as a detail attribute. Promoting that back to a point attribute, now I have P, dist, and max dist. We already know the minimum distance, right? Minimum distance, if it's at origin, would be 0, if the point was right in the middle. So you can leave that at 0. And just refreshing that and giving it a variable mapping here. Okay, now we can set the percentage. So this is a VOP that uses a ramp. Who's used VOP's ramps? Cool, cool, cool. Okay, so basically this is how we control our dispersion into our delete. So if you wanted a lot of points in, actually, say we wanted no points in the middle. There we go. And we want a lot of points in an outer ring around it. Okay, so we can control exactly what the distribution amount of points is based on this lookup curve. Okay. Okay. So this is this VOP's network is taking in dist, distance from the center. It's taking in max dist. It's dividing it. So then you get 0 in the middle and 1 on the outside. Okay. Now we're ramping it and spitting it out to an attribute called pers, or a short for percentage. Okay. Now to ISO by a percentage, this is a little trick I had to figure out many years ago with a random expression, and a lot of people haven't seen it. So what I'm doing here is rand expression, and we're going to do a random value for the $PT. Now we want to test to see if this random number is greater than the percentage that we give. Okay, and that means that it's going to take 20. Actually, this is useless. We're taking the percentage of the attribute we just made. So actually, let me spit this to color just so it makes a little more sense. Okay, there we go. Okay, so you can see how it's white in the middle and it gets dark as it goes farther from the center, right? And this is according to our lookup curve. So if it's in the middle, it has a very, very high likelihood of being a greater value than this random number. The farther it goes out, it has less and less of a likelihood of being greater than that number. So if we have a random expression in here, we can say, is it greater than percentage? And this will almost always be greater than the percentage. This will almost never be greater than the percentage. Okay, so that's where this deleting expression makes sense. It'll give us it'll keep the most points in the middle and discard most of the points on the edge. Okay, and anytime you need something to spread exponentially outward from a cracked surface, this is a good technique to use. It's this kind of a distance-based percentage. Okay. All right, so now I'm going to copy these circles onto our points on the wall. That's why we got the normal back there, is because our other normals were all, according to the particle, these normals are coming out from the building. So that's an ideal thing to copy these on, is to the side of the building. Let's see, get the, there we go. Okay, so these normals are aligned at the side of the building for their copy. All right, and then there's our fracture geometry. We would fracture it. This is an ideal method opposed to fracturing the entire surface, because that would take a lot longer, and we also wouldn't get the art detail of having high detail going into low detail, or bigger cracks, I should say. Okay, that's simply cashed out, writing and reading. Okay, so we don't need that for now. Now, here, we can also make an attribute based on all those distance attributes we just calculated, that percentage attribute. So if we were to test that by color, I'll show you guys what I mean. So if we want a hole in the middle of something like this, let's just say, is percentage less than 40% of that percentage attribute we just did. So 1 minus hole, 1 minus hole. Okay, we can set what we actually want to destroy based on that percentage attribute that we inherited to our fracture. So, okay, we want a really small hole, or sorry, really big hole. It could be, if the percentage is greater than that. I guess I could, let's see, I could switch it and delete non-selected or whatever, but here's really small holes, barely noticeable. So this is how we can take control of a system like that. We'd be copying our attributes we use to fracture it onto the geometry and then doing tests based on that. Okay. All right. Now let's see. Okay. Now here is a. I'm going to set us loose on fracturing in just about 5 minutes, but I just want to. We probably won't get to. So we'll basically just have like about an hour or however long, half an hour playtime with the system and ask any questions or explore the system or whatever. But this part, I think that a lot of these techniques up here, most of us are probably familiar with or have seen before, and here they're just kind of laid out. This is where it gets into some actual complicated SOPs processing that I wanted to show, or at least demonstrate. So on this is a circle that I'm making out of just lines. Okay, so starts off as a fraction of a circle, and I'm just let's see, what am I doing there? I'm just rotating it to the middle and then copying it on different axes. So we have like an open fractured circle. Okay. Connectivity, color by connectivity, resample to make lots of points. Okay, and transform to stand it up on the axis for copying. Okay, nothing fancy there. The main thing to make note of here is the class attribute, because it'd be different for each of these circles. Now, when I copy circles onto this, I'm going to use these lines as things to push the cracks away from, to create these fractures that go out from the center. Okay, so I can put a noise pop on them. That's a Voronoi, or not a Voronoi, rather, a Antilea's flow noise on this guy. And here I'm extruding each surface and making it a solid rim, like that, using the skin. All it's really doing is just, well, let me go through it once. I'm shrinking it a bit, deleting the primitives, making a line around it, pushing it along the normals, merging it together, using the skin stop to connect them, and fastening it to recreate the normals. And these normals are going to push the cracks inwards towards them. Okay, because before they started off having these kind of normals, and that would just push it out. We're going to use these normals on here to push them inward. Okay. All right. So we've got these really, really weird looking things. We've got a fractured surface here. Now, using these pinwheels, they look like those pasta things that you've seen. We're actually going to push it away from those based on the mode of these guys here. All right. So how do we do that? Well, okay, we want a unique class for each one. Scatter points on them. Then I'm going to get the nearest point from each piece, and I'll gather the class. So each of these things has a class on it. If we wanted to test that class, you can look at it and see it looks like that. Okay, so not terribly organized. Actually, did I already? I think I might have already done that one. Ah, okay. Okay, that's what the class looks like at first. Okay. So if we just push this away based on class right now, based on the normals, it would be a mess, because the classes are different for different points. How do we actually make the class the same, the inherited class, the same for each of these points that it just inherited? And the way to do that is with a loop. Okay, so I'll explain this loop a little bit more in detail later, but basically this is just looping, looping, looping. The important part about it is that it's getting the median of the class. It's going to gather the most common occurrence that it found for that. So after we do that for each piece, now all of these guys are the same. Okay. So it won't have one point being pink and one point being green. It would all be the same thing that it gathered based on the most common occurrence. Okay. And let's see. I think I'm just setting attributes here. Okay. So yeah, it takes these wheels and it will set each piece to one of those wheels and push it away from the normal. Okay. Now for this guy, I'm moving them back. But how do I know what direction I move it back? Well, it'd be the normal of the hit. So the normal of the building, I'd move it in the opposite direction of the normal. Okay. So back here, we have the original wall. Here, we have our process geometry. And now, this is the system. This is not time dependent, and this is not time dependent. here's the first place we're going to introduce a time dependency. We've got all of our fracturing done. We've got all of our procedural system lined up. It's going to fracture in the places it got hit. It's going to push it away from the wall and away from the normals of our copied circles. And pretty much, where's the time? What does the time dependency do? Well, it'll blend between this and this based on two things. Okay, it'll blend based on, so let's see, impact frame. So if the impact frame that it inherited from the point is greater than the current frame, then it would activate that. It would blend from the second input. If not, it would use that percentage attribute to blend. So I'll just take this out. You can see what the percentage attribute does. Okay, so the percentage attribute is what actually creates the creates the blend. Remember how it was the greatest percentage in the middle, and the percentage went out from the sides here? So if we just didn't do anything, it wouldn't be time dependent, and it would just blend based on that percentage. So way back in the other part of the system, if you wanted to have like a bigger spread or different spreads in different areas, we just adjust that ramp. But we want to make that a time dependent thing because we want it to actually do that when it gets hit. So now by testing against the current frame, it would fracture when the frame fractured. Okay. Alright, now I'm just going to kill based on the whole attribute. So if the frame is greater than the impact frame and whole, then set to 0. And then it would just delete the inside pieces. And there we go. That would of course be merged with the unprocessed part. There we go. And then we get a procedural system to crack the wall. Okay, so I know that was a lot of stuff. Let's spend however long you'd like to remain, and I'll go over any part of that system. If not, just take that system, study it, use any tricks you can, and we'll get to the particles part and the dynamics part tomorrow. All right, so, and actually this does touch on a few repetitive ideas from yesterday. So, in this node, in OBJ, building rock particle system, I should have hidden the nodes, apologies. I'll just escape out of that there. Okay, I'm merging in the building. It's really just for visual reference. We don't actually need it in this node. So I've got template on. The points I'm merging into. Now these points are the sticky points that we looped through yesterday. So they have their impact frame already present on them. So here I have 3 blasts. You guys can modify your tanks and have whatever blasts you'd like to test out your effects with. Okay. Now, so that's that. I'm simply adding a attribute for the position here called center, and I'm then making a time-dependent thing to isolate them based on their impact frame. So we can see them appearing as they impact with that. Okay, now, so we've got the impact points. We need to put, we could either use that directly into pops, which sometimes works, but what I found is almost always good to do in pops is to start with the points that are actually going to be birthed in SOPs level. It's a lot harder to control it once we get into pops because they're not really geometry tools. They're not really built for orientation and direction and distribution. They're really just built for once they're alive, then do stuff with their motion, and that's okay. That's what pops are for. But here's the geometry process that we are using as a precursor to pops. So I'm starting with the circle. Here's my circle. Scattering points on the circle. the thing we did yesterday, I just copied and pasted that here, so this is another chance to revisit that. I'm getting the distance from the center of the circle. So position, length of the position vector.
Are you just missing two?
What's that?
Are you just missing two?
Yeah, it was, yeah, I think 2 students, yep.
Awesome. I was just wondering.
Yeah, they can,
You start to go back to work.
yeah, well, I'll brief them on the stuff that we went over if they show up. Yeah, so, okay. So yeah, importing the position, getting the length of the position from the origin. So the middle of those x, that x right there would be the origin, so we're getting the distance there, length, and then exporting it as an attribute distance. Now I'm promoting distance from a point to a detail and getting the maximum distance. Looking at this guy, the maximum distance is 0.709, so it's probably one of these guys way out here. Okay. Now promoting that max distance detail attribute back to a point. So now we have distance and max distance on all these points. Now when you attribute promote something and you change the name, it doesn't have a local variable associated with it. So all I'm doing here is I'm refreshing that attribute so we can easily access it with a $sign. And then the magic happens here. Actually, I think the thing we should start off with is by recreating this VOPS network today. So we can save this part just to viz through it just so you understand the process at desk. But for starting today, I think we should start with this VOPS network that actually allows us to control the distribution of our starting off point cloud. So this is the set percentage VOPS network. I'll make a new one. Okay, and yep, that's pretty simple. Okay. Okay, so I'm going to, we have two attributes. We have dist and max dist. So dist will be different for every point, and max dist will be the same for every point. It's the maximum distance of all of them. So I'm going to import attribute, float attribute, dist. Then we'll also import max dist. Now if we want the percentage that this particle is away from the center, all we have to do is divide this by this. So we'll use a divide sum. And dividing this dist by max dist. Then we would do a ramp. And I remember when these things first came out and I was like, yes, I don't have to do an animation curve in a point stop anymore, which is really, really slow. We can do this blazing fast float or color ramp, and it'll do awesome things to point clouds really, really, really fast. So I'm going to set this to a spline ramp, and I'll call this dist ramp. You can call it anything really. And then I will export that attribute, a new attribute, from this ramp. So this would probably be, I should mention all of these, if we divide distance by a maximum distance, it will always be from 0 to 1. It'll be a percentage. So that's, you always want 0 to 1 before you feed it into a ramp box. Okay, so here's my ramp, and then I'm going to export an attribute, and we can call this, what did I call this in here? I think I called it percentage. Yep, pers. Okay. You can call it anything, just make sure you know what you call it. Okay. And let's pre-visualize that with the color attribute. Let's actually, it might be easier to see in red. At least I always think it is. So I'll do a float 2 vector. So we'll use the complement of our attribute going into the blue and green channels, and we'll just use 1 for the red channel, and that'll give us red if it's a high value and white if it's a low value. Okay, so right now we have an even distribution of white to red. Let me make these guys a little bit bigger in the view. Point size, there we go. Okay, and now we have really good control over this. So if we want the center to have high values, if we want a lot of particles to be emitted from the center, and then we don't want any particles to be emitted from the outer place, then we would adjust the distance ramp inversely. So basically we would keep a lot of particles in here. Now with an impact, like a bullet hole impact, we probably wouldn't want any particles coming out of the center. We'd want particles coming out of the outside and then tapering off as it got farther away, but we wouldn't actually want any particles directly in the center. And the reason for that is if you blast the wall with a bullet, it wouldn't blast directly backwards, would it? Okay, so that makes me think my distance ramp should look something like this, where it's not present in the center at all, and it would ramp up slowly and then quickly, and then it would taper off slowly again in an exponential way. And this just gives us this added level of control over our particle effects to use ramps and things like that. So now, if we isolate this by percentage, we would get the most particles being emitted from this red zone. So in a delete SOP, I would go points, delete non-selected, random $PT is greater than percentage. And that's the opposite. I would do less than percentage. Okay. There we go. So we're mainly keeping the red points, and we're mainly losing the white points. As we adjust this ramp, we can see the changes take place in our point cloud. So we want a lot of points in the middle again. There's our points in the middle. Okay, so that gives us a lot of control there. It's also, you can turn up, this will ultimately control the number of particles and rocks that are emitted, but for testing you could crank this value up quite a bit. Bob's is plenty fast, so don't worry about it. So now we can see we've kept a lot of points, lost a lot of points there, lost a lot of points there. Okay. So let's give this VOPS network and delete SOP a try, and then we're gonna jump into doing the actual particle sim. This is where this is going though. Let me set that scatter back down to a reasonable number. Okay, so basically these disks are going to be copied as these are hit. There we go. So those will be our particle emission points. And if we wanted to, we could make the seed of this, even we could have a different seed for every frame. If we wanted a different distribution for every frame. Okay, so let's give the VOPS network and delete SOP a try. Okay, this is in OBJ building rock particle system.
Will this work if your object isn't at origin?
What's that?
If your object isn't at origin?
Yeah, it is starting off at origin, yeah. So the circle is starting off at origin here.
Yeah, but if you're trying to do this on something that isn't, you have to put it back to origin and bring it back over?
No, you would just need an attribute for the origin.
Okay.
Yeah, so in our VOPS network, we could go instead of, that was a great question by the way. Sorry, I should have opened that up for questions. So doing the distance here, instead of using P, which presumes that the center is at the origin, we would go, instead of a length VOP, we would do a distance VOP. And we would say, what is the distance from position to center? The center would be an attribute.
Cool.
Yeah.
That makes sense.
Could you do that with like a vector setting 0, 0, 0?
Yeah, we could. So here we'd have position going into here, and here we'd have a constant, in this case, a vector, and the vector would be, well, here I'll make a parameter out of it and we can test it moving around. Okay, so parameter is vector. Okay, and then I'll use that. Okay. So here we have, this is the same thing because our parameter is 0, 0, 0, but if I were to move the y up, you can see that now it's the distance from that. So whether it's an attribute or whether it's starting off at the origin, it's the same technique.
Cool.
Yeah. All right, only a day getting there, huh? Okay, so, all right, everyone's seen CopySop before. Let's see, let me view the building again so we can see what's going on there. Okay. Now, we're going to question or redefine how we use the CopySop in a little bit, in about, I'd say, half an hour or so. But let me just say what I think a good use of the CopySop is. You get into learning Houdini, and the first thing, myself included, that I teach new people in Houdini is the CopySop, because the CopySop is probably one of the single best procedural tools of any software package in effects. And you know, once you have it, you just want to do everything with it. You want to copy like all these stamps and random variations, and our scenes end up taking 10 hours to cook. So a CopySop, I think, is very, very useful when we have something that's very light going into the first input and a collection of very clearly defined informational objects going into the second input. That's different from probably what you learned when you started Houdini. When you started Houdini, you learned, okay, we can take this big asteroid and copy it onto 1,000 points and look at this giant field of asteroids now. That has its place, but I would say that place is more point instancing now that we're more intermediate or advanced. So right now, I just have probably a single point going into here at any given frame, and we're just copying particle impacts onto these. Okay. Let's see what are the frames here. Let me just make sure everything's going through. At frame 28, 42, 73. Okay, so here we have one on 28. Boom. Here we have one on 40. Okay, so there's our impacts. For right now, I'm simply copying the normal to each of the points going into it, so that it goes out from the building, and I'm copying this center attribute, so each point knows where it's being copied from. Each event knows where it's being copied from. We're going to use that later in the CopySop down the road. Okay, so now I'm going to set the normal, and one thing that I think that most people effects-wise would benefit from is really good ways of manipulating normals going into particle effects. So this is a good tool. Open it up and play with it for a few minutes as we go back to our desks. Basically, what I'm doing here is let's reset all this stuff. Okay, so we're starting off with normals. Now here I'm doing an outward spread. How am I doing that? Well, I'm using that center attribute that I just copied in. So the center attribute's going in here, position's going in here, and I'm subtracting that to create a vector. And from there, we can use that to mix, using that mix outward parameter, just mixing what was the normal versus that center outward normal. And that's really good at creating impacts. So that's that. So we get a good outwards mix going. Let's see, how do we want these particles to fly out? Okay, something like that maybe. Now, the next thing is randomness. So randomness in VOPs, now I'll be completely honest, my Vex is awful. I know very little Vex, and the reason is because I haven't really needed to learn it yet. The second you really start doing hardcore coding in Houdini, I think you kind of have to make a choice between, do you want to be a pipeline TD or an effects TD? But what I always do is I'll just get a point jitter and I'll say, okay, I'll dive into it like, oh, here's my random expression, so I just copy these out of there. And the vex is really simple. It's just setting a variable name here, and it's piping it out. But since I'm some vex illiterate, I just copy stuff from there into my that VOPS network. So here's my point number. I'm turning it to a float. You can add a seed in here if you want to. So if you want to set different seeds, just pipe them into an add VOP. And from here, I'm just making a random vector. So all of my hscripts rands, I'm just adding something different to the seed on the second and third vector, putting it back to a vector, fitting it from 0, 1 to -1, 1, and that'll create a completely random set of vectors. And then normalizing. That gives us completely random values for vectors. So adding in some randomness. Yeah, there we go. Let's get some randomness going. All right. Something like that, maybe. Okay. Then the amplitude. How big do we want this effect to be? So that's pretty simple. That's just a multiplication, right? It's taking our normal and it's multiplying it by a float. That's it. Nothing special there. So how big do we want that to be? Good SOPs control in that. You don't have to want to fuss with the source pop. You want to keep it in SOPs probably. And then the last thing, which I think most particle effects could benefit from, is a second randomness that mixes the amplitude of these. So on one hand, we have our full force vector, and on the other hand, we have a random multiplier for that vector. So just before it goes into the, oh, that's the amplitude, my mistake. Just before it goes into the final amplitude, I'm mixing a third set of noise with it. So it's taking the original normal, putting it into the first input. It's taking the normal multiplied by random into the second input, and then we're mixing those two things together with random amp parameter. So now what we can do is we can say, okay, do we want all of these particles to be this forceful, or do we want only half of them to be this forceful? And if I want them to be completely random, but the maximum being that, now you see what happens. I'm randomly decreasing these guys along their own vector. Okay, so that'll create a really natural spread of intensities along our particle effect. The problem with doing all this in a source pop is we simply don't have enough control. This gives us a lot of control over the impact and stuff. Okay, so take a few minutes and play around with that. Now, here's a VOPS, or a subnetwork for particle attributes. We need to do a little bit of preparation before we go into this POPS network, because this POPS network is special. It's going to want some rotations on it. All right, so rot. What I'm using is I'm using the normal and the up vector. Okay, and it doesn't have an up vector yet, I don't believe. Okay, so I put an up vector of 0, 1, 0, and here I'm doing two cross products, and the effect that has is that it just sets the up vector to, if we were just pipe in the up vector right now, okay, it just starts off as like a normal and then up going 1, up and Y. Doing these two cross products, it's not a science really. It's just I set it to the cross product of that and the up getting this vector. Then I cross it again with using the right hand rule. It would probably go to the northward or upward direction. And now we have just like intelligible up vectors to use. These aren't mission critical. They're just a good habit to have. Always go with normals and up vectors into a particle system. Okay, now I'm giving it a much more important attribute, the rotation attribute. So everything I throw into my particle network is going to have a rotation already on it. We could do this in pops too. We could add a rotation attribute, but I find that you have more control over it in SOPs. Particles, you'd have to do it on every iteration and all kinds of stuff. VOPs, it's very easy to use and you can just do it once. So here I'm using a look at VOP. Who's used look at VOP before? Nobody. Okay, this is really, really useful. Doing transforms in VOPs will free you from using a transform SOP, brutally slow and terribly inflexible, choosing between a transform SOP or a point SOP. And a point SOP, you don't really have control over rotations or anything, do you? So you're just really moving point positions around. So one of the key ways that I will go from normals and up vectors, and those are, we've all done copy SOPs with normal and up, right? Yeah? Okay, so to take that one step farther, we have normals and ups on here. To turn that into a full-fledged rotation matrix, I know I said the M word, don't freak out, we're going to learn what that is. All right? To go from a normal and an up, we have a plane already, don't we? Those two vectors create a plane, and that is a full-fledged rotation matrix right there. We have position, which is where the point is, and we have orientation, which is where these two vectors is. So that's all we need to have a full-fledged rotation matrix on each point in our VOPS network. And after that, we have complete control over rotations as well. All right. So what I'm doing is I'm using a look at VOP to make that. I'm using the starting position of 0, 0, 0, using the 2 location of the normal. So starting at 0, which way am I looking? Looking towards the normal. Which way am I tilted? I'm tilted the up vector. That's what the look at VOP does. Okay, so that's the easiest way in VOPs to turn your normals and up vectors that you're always used to working with in particles and stuff into a matrix, is with a look at VOP. So here's that. I'm just putting the up vector that we just made into the second input. We're going to use this more, so don't worry about messing with it right now, but we're going to use it throughout the day here. And it'll really come in handy. All right, so now I'm just turning this 3x3 rotation matrix into quaternions. And quaternions is just how POPs keeps internal tabs on its rotation attribute. So I'm turning it into quaternions, and I'm exporting it as what POPs uses already, which is ROT for rotation. So now we have on this guy rot 0, 1, 2, and 3. All right, that's going to be the orientation of our particle as it gets birthed. Okay. So we've got our rotations, we've got our normals and up vectors. So that's all this guy did, was do all that groovy stuff. It turns ordinary particles into exciting particles. All right. Now I'm going to set a random rotation axis. Just because the particle is rotated this way doesn't mean I want it to spin that way. All right, because there's nothing more boring than particles that are spinning all along the same axis all the time. So it's cool enough that we got it to spin, but we want it to spin in different directions, right? That's going to be a random effect. And if we did want it to spin along the normal, that's easy. We would just set it to the normal, right? We'd set it to its current rotation attribute. But okay, let's make it random. So here's a random vector. Let me see, what is this? Normal. Let me just hide the up vector here. Okay, so all this point SOP does is make a random normal. Could have done this in VOPs too, I don't know why I didn't, I just used a point SOP. Okay, now I'm setting this, I'm normalizing it and setting it as the attribute axis, the vector attribute axis. Okay, now I'm just copying that onto, with a copy attribute copy, I'm just copying axis onto our points. Okay, so now everything has this axis which it will rotate around, called the axis attribute. Right? So we have, on these particles, we have the normals that go in the direction we want them to go. We have intelligible up vectors. We have the rotation axis made of these normals and up vectors. And we have a random axis attribute that's going to rotate around when we throw it. And once you have these attributes going into your into your system, as well as these normals to throw intensity, and of course the intelligent distribution, meaning the position stuff we just did. Now we have a lot of cool information going into particles, and we don't have to clog our particle network making all these random stuff just to get good positions and trajectories and stuff. We have all that ahead of time in an easy SOPS user interface. Now all we have to do is send it into particles, and it should just do magic for us. Okay, so those are key attributes subnetwork. Take a few minutes, check out the normals, the way we messed around with the normals here, and then the P attributes, just to familiarize yourself with it. We'll come back to it. All right, so got our final effect going in here. We've got our ground going into here, and here's our particle send. Okay. Oh, and I should mention, I don't know why I had that attribute up there. We don't need it. With that spare parameter up here. Just ignore that. Okay. Okay. So source pop. All right. Easy enough, right? Okay. They're going in the directions of their normals. Can anybody give me a reason why I'd want to source the initial velocities from the normals and not actual velocity attribute? Well, the normal is a kind of a record of what direction it originally was birthed at. Right? If we use the velocity attribute, the particle network will overwrite the velocity attribute the second it starts changing direction. So having a normal for your births is a good way to keep track of what direction it originally went. Okay, so if you wanted to cull, say, okay, well, I like my particle effect, but I want to get rid of the particles that shot upwards instead of downwards. You have an easy solution to that, even after it's cached to disk. Okay, if you use velocity, then it would change on every frame. These normals will remain constant. All right. Okay. Now, I'm going to initialize the attribute axis. Okay. Also, to create a local variable, there's this little checkbox on the source pop that most people will kind of overlook from time. I always forget about it too. If you check this box here, create local variables, it means that the source pop will connect all of these variable mappings to it. Okay? So that's always good to have on unless you're explicitly not using them after that. Okay, so here we're refreshing the axis attribute. And our good old P state, remember that guy? These are going to get stuck to the ground eventually. So I'm using the stuck attribute here. And gravity. Okay, so let's see the result of this. Okay, that's pretty cool. As we play with this particle effect, go ahead and adjust your... okay, impulse birth rate is set to number of points. That's all fine. I would adjust your inherent velocity and your variance. It can give whatever good result, but remember that you can also adjust the velocity here in your amplitude. So it's probably better to adjust it up here in the amplitude. Okay. Now, here's the part some of us might not have seen before. The angular velocity pop. And the reason I never used this when I was starting out is because I didn't understand it. It said it put angular velocity on particles, but I didn't see anything happen. Okay? Well, you have to have a rotation attribute for it to work. What this guy does, it manipulates the rotation attribute. The way guys at Rhythm were always rotating particles is they would actually use a rotation pop. I won't say everybody, but most of them that I learned from. So they would use a rotation pop, and they would do this fit. So they'd fit the rotation of the particle to the lifespan of the particle. But the problem with that is that if a particle is alive longer, then you have to adjust your ramp. It affects how fast it spins. It's not a very natural way to rotate particles. The angular velocity, however, that's actually spinning it. It's the rotation is like here I'm gonna pretend that this this backpack is a particle. Okay, so a rotation pop, I'm holding onto it with both hands, and I'm spinning like this. Okay, now an angular velocity pop, I'm just doing this to it. Okay, so it's actually more natural. We have to worry about it less if we just hit it once with an angular velocity versus having our hands on it the whole time and spinning it the whole way. Right. So that's why I like angular velocity now. So it uses the rotation attribute. Now I'm giving it a random rotation here. So I'd encourage you guys to copy from this particle network as you set up your own effects at home or in the studio. I'm going to fit random ID 0, 1 to angular velocity 1, angular velocity 2. That's these numbers. So it will go anywhere from an angular velocity of 1, which is almost unnoticeable, to an angular velocity of 2000, which is 3 revolutions per second. Okay, or 360, it's like 5 revolutions per second. Okay, so angular velocity, yep, that's my range of angular velocity. How do we view it? Turn off the normals and turn on these little dudes right here. Okay, this particle axis. Yay. Okay, no, I'm not viewing it yet. Okay, there we go. There we go. So there's the rotation. So they have random rotations by ID, random angular velocities, so manipulating the rot attribute, that quaternion attribute we just said. Now, what is it rotating about? It's rotating about our axis. If you did want it to rotate about the normal, you would just change this to nx, ny, nz to control where your rotation happens. Or if you wanted them to rotate like hops around the up vector, just change this to the up vector. Okay, but this is a random axis right now. Cool. Okay, now, positional drag. You can have a drag pop. Has everybody used the drag pop? It, by default, does linear velocity, and I like to keep it that way for linear velocity. I don't want to do both at once. Why not? Oh yeah, you want to control that separately, right? Yeah, so the position something slows down almost has nothing to do with the way the rotation slows down, right? Especially in pops where physics is not really present. So here's our positional drag. There we go. It's just adding a little bit of slowdown as it goes. Probably unnoticeable for this kind of an effect. Now, for angular drag to work, we actually need a second attribute, which is torque. So simply, I thought it was broken until I think it's Jason Iverson told me, oh yeah, you got to add the torque pop. Like, oh god, I wish I wouldn't have spent a week on that when I could have just knew about that. Okay, so yeah, whenever you want to do angular drag, it won't by default work. It has to have that separate attribute called torque, and only thing you have to do is drop it on. That's it. You don't have to do anything else to it, just drop it on, because it uses that to keep track of itself. If this was a more modern, Pops is ancient, but if it was more modern, it probably would have added it automatically when you turned on this checkbox, but it doesn't. So before you do this, add the torque pop. Okay. Okay, so we add our torque, and then we can do angular drag. And angular drag is awesome because now I don't have to do some weird ramp in my rotation pop to affect how they slow down. I can add my angular drag and forget about it. So I'm just applying angular drag, 0.3, and they'll slow down over time. Let me turn off the gravity and the velocity. Let's see that happen. Okay, they're spinning pretty quick, huh? Let me make these guys a little smaller. Okay, so spinning a little quick. Let's increase this angular drag. There we go. Isn't that cool? Yeah. Let's have a little more gradual slowdown. Yeah. And if we wanted to, we could add randomness to this. So we could say fit ran ID 0, 1, 0, or 0.1, 4. And now they'll slow down at different times. Okay. But for right now, since they're all rocks for this effect, I'm just going to add 0.3. Okay. Alright, so we have angular velocity, positional velocity, gravity, angular drag, positional drag. Okay. Alright. It's starting to look like a pretty good effect. That's what people normally do in DOPS. And it's a really big waste of resources, I think. Okay. Alright. Now, collide. And now this isn't as a collision in POPs is kind of a lost art because we are so used to going to DOPS for these things now, right? But we can do most of our bread and butter effects work with a network like this and a collision pop. Okay, so this is our ground. Now, the only thing that DOPS gives us and particles doesn't really give us is when it hits the ground, we can make it bounce easy enough in pops, right? But what DOPS gives us is it'll hit the ground and then it'll rotate accordingly as it hits the ground, and that's not really what pops does, right? And it can't because it has no sense of geometry collisions. But we can trick the eye good enough in 90% of situations. So I'm going to trick the eye, and I'm going to say, if it hits the ground, slow down your rotation. Okay? So collision pop's pretty standard. I've got behavior of 0.1. So what that's doing is it's a collision normal and tangent of 0.1. So basically what that's doing is it's hitting the ground and then it's bouncing 0.1 up of its initial velocity. Okay, so hits the ground going this fast, and then it'll bounce up at 1/10 of the speed at the tangent of that, which is that angle. Okay. Now, to add a little bit of extra realism, which DOPS would also give you, I'm going to trick the eye again, and I'm going to say, don't bounce the same height for everything that hits the ground. Okay, and I actually should have copied this guy to the second parameter as well. Okay, so it's going to go bounce anywhere from, I would say, a full, 0.15 bounce, which you could expect from a really aggressive rock hitting the ground, to a really, really low bounce of 0.01 rather. So not everything that hits the ground will bounce the same height. That's a really important aspect of realism that you have to program into pops. But it's pretty easy, right? It's just a fit expression. So we've got that. Now, the next thing on this is I believe it has a group somewhere. Actually, no. Okay. If you wanted to, yeah. Okay, if you wanted to, what you could do is you could make a collision group here. I didn't have that on here, did I? No. Okay. Source group behavior. Okay, here's the collision group. All right, so I could say did collide. I should have put this in the example file. So I'll go around at your desks and check to see if it's working for you. Okay, so this is a new group in pops, did collide. And now, just so we don't error out, I'm going to say preserve group, and what that'll do is it won't actually get rid of the group if none of them are present in the group, so our pops won't error out and say we can't find the group. Okay, so did collide. And what you could do is you could do a very extreme angular drag. Okay, so I can say extreme drag, apply to angular velocity, and then I can put that pretty high. But it's only going to really do that extreme drag on the rotation if my source group did collide is present. Okay, so if it's just collided, then it'll apply a lot of angular drag to it. And that's what something like this will do. So go ahead and experiment with that. Okay, so it'll really slow down. If we do it really, really high, then they'll stop rotating once they hit the ground. Let's see. Yeah, see that? Otherwise, if we don't, they'll keep spinning when they hit the ground, which is unnatural, of course, right? What I did here is I simply said if it's stuck, then multiply the angular velocity by 0.5. Otherwise, keep the angular velocity. And what that'll do is it'll just exponentially decrease the angular velocity as they're on the ground. So it's kind of like it hits and then it rolls a bit. And that's the visual effect you'll get from that. So you could use both of these in tandem if you want. Okay. There we go. I'll put that back down to 1. Okay. Now, one last piece of information. By default, if it's stuck, even though it's stuck, it'll still have velocity on it. And that's because particles doesn't really deal in physics, it deals in attributes. So that's really the mindset of early days of particles. There were no physics, it was only manipulating this logic network, and any attributes you put into it were meant to resemble physics, not be physics. So these guys already have velocities on them, and they'll keep their velocities as we. I wonder if I can actually view them in here. Yeah, okay. These are the orange guys here are the velocities. So they'll actually keep their velocities as they hit the ground. So they won't go away even if they're stopped. So I just have to do one more piece of logic. If stuck, then 0. I'm just setting my velocity to 0. Otherwise, keep the velocity. All right, and that'll just make it a good system that won't give me problems later down the road. Now they go to 0. And that's some pretty natural bounce and rotations and stuff like that for a POPs network. In studio dailies, I'll often showcase particles as dynamics because they'll ask, okay, is this realistic simulated dynamics, whatever? Like, yep. And it's not, it's particles. Don't ask, don't tell policy, right? Okay, so yeah, if you can get away with using particles, it'll make you won't have to spend hours simming on the farm. You won't have to simulate heavy geometry. You can just pass off your effect as realistic physics, and particles are so much easier to manipulate and control than dynamics are. You're going to get these occasional 2 rocks out of your brilliant effect. You'll always have 2 rocks that'll just fly out into space, and you'll probably have to select them and delete them, or you'll have to change your settings, and POPs you don't have to do that. So I'd say about 50, 60, 70% of all dynamics effects that people do on a daily basis in a studio can be done with particles easier than they can be done with dynamics. Now, that's not to say that dynamics doesn't have their place, because they're necessary for photorealistic stuff, as we'll get into later with the Jeep. But you can't do that with particles, it just won't look real. But rocks, yeah. Leaves, yeah. Don't go to dynamics for that. Use particles. Okay. They're easier. All right, so here's our particle sim. I think we should give that a shot, and yeah, so let's experiment with the setting the velocity as our normals, take a look at the p attributes, and then go ahead and experiment and reconstruct this POPs network and experiment with the results we get out of it, just to really understand the process. And I'll help you guys with seeing the attributes and all of that stuff, of course. And then so that'll be what we do for the next lab here, and then after that we'll worry about getting geometry on it later. Cool. Any questions from that stuff? Okay, so one thing I forgot to mention, which was actually a pretty crucial part of the system, I forgot to mention that the angular velocity is only set on the first frame the particle is alive. Okay, so if you set it the whole time, it's not going to work. You only set an initial angular velocity. And the way to set anything initially is by creating a source group. Okay, so on this source pop, I have a group in here, just born. I'm using that group to apply any attributes that are only present on the first frame the particle is alive. So that applies to angular velocity. It's using the source group just born. It's not going to apply that if it's not just born. Okay, so yeah, that's a really crucial part of the system, and I just overlooked it. Okay, so cool, fun with pops. Now, pops are great, but unless we're doing snow or little bits of stuff, we're probably going to want geometry on the pops, right? So I'm just going to demo this system, and then we'll have a little bit of time for it to sink in, because we've all been doing copy stamping for a while now, right? Copy stamping is fun, but these days I almost never use it. And also, so in a situation where you have like 5 objects and you want very good variation on those 5 objects, that's really what I think copy stamping is good for now. If you're using copy stamping to impart randomness on things, I would now suggest, once you learn a technique like this, try to use a technique like this. So who here have taken 5 rocks and done a switch swap and randomly switched between those 5 rocks? Okay, now that's a good thing to do, but what happens when you do 10,000 rocks? It slows down, right? Okay, or maybe you're doing a lot of different types of rocks. You don't want to increase that too much. It's going to take forever to switch and compute and all that. Now, what this system here does is it takes and it can impart, it takes one simple piece of geometry and imparts an infinite amount of variation on that geometry without any hit to performance. Okay, so what I'm doing here is I'm taking, let me get rid of the template stuff here. Okay, so here I'm just deleting the transformation attributes off of it, the particles, giving it a point number attribute. So the point number attribute, $PT, I'm going to use that point number to determine which particle I gather. Okay, so every particle is going to have a point number in here and in here. It's always going to be the same number, right? In fact, I could probably stick it in a different place in the network just to use it. Okay, so everything that goes into this copy loop is going to have a point number, easy enough. Okay, there's never going to be a different amount of points copied than there will be present. All right, so no X-form data in this one, no rotation, no velocity, no p-scale, no and no up. The copy SOP uses those things to orient and position the particles, or the copies, right? So we don't want that. Okay, now, here's where the funky stuff starts. Okay, I've laid these out on a grid with a point SOP. Actually, it'd probably be even quicker with a VOP SOP. This is completely disregarding all of our awesome sim, and it's putting these guys in a position by ID. So ID modulus 10 in the X, ID modulus whatever in the Z. It's just laying them out on a grid. pretty much, or no, this is a floor. So pretty much what we're doing is we're doing ID times 0.1 and then rounding it down. So that means that every 10 IDs, it'll go one step farther. Every 10 IDs, one step farther. Okay, so all of our particle effects, even if they were born and died and stuff, they would just be laid out on this grid and they would never change what position they were because we're using ID to do it. Okay, now this is unnecessary too. You could have them all in the center as well, but that's a different way to do it. Okay, and now I'm just saving the copied position here as an attribute called offset. So the value for that is tx, ty, tz in there. So I'm just recording in an attribute where in the grid they are. That's it. All right, but this doesn't take a hit, does it? Like this isn't really like a switch stop. This is just repositioning particles. It's as fast pretty much as the actual stream itself. So unless we're in the millions, this isn't going to present a significant slowdown to our processing time. Okay, now here's my geometry for a rock. If we wanted even lower res geometry, I would just subdivide it less. Okay, but it's just a box that was subdivided. Want it less, do that. For right now, this is fine. And I'm using a copy swap, copying over point num and offset, but notice that there aren't any stamps here. Stamps is really what slows it down because it has to switch swap or delete swap everything that's going into it and recook everything up the chain in the stamp operation, and we're avoiding that process. So what's happening now is we're copying these spheres to the point position, but they're not oriented differently. They don't have any stamps on them. The only thing that's different about these, other than a minute difference in position, is that they have a different PT num attribute, and they have a different center or offset attribute. So this guy has a different offset attribute. This guy has a different offset attribute. All right, now here's where we impart our infinite amount of variation. Okay, this is just one operation, but it's going to give an infinite amount of variation because I'm using position to impart the variation. I'm not using switching or random variables or anything. I'm using a one single VOPS operation to give randomness in position. All right. Now, using PT num, now I'm going to transform them into place. So every single rock is completely unique, and it doesn't take a hit on processing power. Okay? So now we are going to rethink how we use the copy swap from now on. Now scale is important, but the particle scale can be imparted by on the point level, right? So here, I'm doing my particle scale just, with a ramp, just giving it some good variation, the p-scale. So this guy has all the rotation information and normals and up vectors and rot attribute, velocities, angular velocities. This guy has all the good stuff on it, but it's a point cloud. Okay, so it's no reason to copy that onto geometry each time. This guy doesn't change at all. He just uses the ID and then applies a noise to that geometry that was created there without any stamping. Now the magic happens here. I've redone the copy operation. There's no copy swap present here. It's, instead of a single threaded copy swap, it's a multi-threaded VOP swap. Okay, and all it does is it takes this geometry and it transforms it to the correct point. Okay, so let's see what's going on in here. Okay. Let's do that. Okay, so take, don't need that either. Okay. All right, so let me see that over here. Okay, so gonna make a matrix on each point. Who has anyone ever done any matrix operations with VOPs before? Okay, well we did our first one a while ago, right, with that identity or that look at VOP. Okay, this is actually a real legit matrix operation, matrix math operation. And you don't have to know matrix math. All you have to know is how to do the operations in BOPs, and then you're good. You know just as much as a mathematician about it. Okay, as far as what we're doing anyway. So I'm making an identity matrix. That's just a constant VOP with 16 by 16. And then I'm using the translate VOP to translate that according to the point position. So there's like a little matrix on each piece of geometry, on each little point in the geometry. Okay. Think about it like a null object. Everyone's done the null object. It's got its RTS, all its transformant data, rigging and bones and everything. It's object level stuff, right? Rigging. So imagine you're making a little rig on each point in your geometry. That's how I visualize it anyway. Now I'm going to move those rigs back to the origin. So what that essentially did here, I'm going to extract the transform right now just to show. I'll extract translation data, pipe that into the point position. Okay, all that did is I negated the offset, so it turned my my offset back to the center. That's all that did. So far we could have done this with simple point operations. We didn't need a matrix to do that, but we'll need a matrix for the rotations. Okay. So back to the center. Okay, now we're good to go. We can transform these according to our particles, right? So let's make a particle matrix now. So using the PT_num attribute, that'll tell us which particle to grab, because it's going to grab the point number from the second input. Okay, so this is coming in from input 0. This is on the geometry, PT_num, but then it grabs the second input's rotation attribute, which is the particles. It grabs the second input's position attribute off the particles. It grabs the second input's p-scale attribute off the particles. Okay, so with rotation, I grab my rot attribute, all that groovy stuff with our rotations off of the angular velocity and everything. Now we have that. It's that attribute, the quaternion, right? So now I'm converting the quaternion to a matrix 3, which is a 3 by 3 rotation matrix. It's everything you need to know what it's supposed to be oriented about. I'm converting that to a matrix 4, which is basically just adding position coordinates, even though it doesn't have a position yet. Okay, and now with p-scale, I'm turning that into a vector. Nothing fancy there. It just has to be a vector for the scale amount here. Okay. Here's the position as well. Okay, so first thing is I'm going to scale the 3 by 3 rotation matrix and position added by the p-scale. So now when I had a full-fledged piece of geometry, then that shrunk just a little bit. The geometry hasn't done anything yet. The particle itself, the matrix for each particle shrunk. So we took the matrix particle, we've given it a rotation. Now we've shrunk the rotation. Okay, now we're going to translate the particle by the point position. So now we've translated it into space. Okay, so now that's just the information present on each particle, but we've turned that into a complete matrix. This would be our complete transform matrix on each particle. So we had a matrix for each little point on our input geometry. We now have the appropriate matrix. You could call this the parent. Like if you do a null as a parent to a geometry object, this would be like that. So this would be the parent of what we want to transform it by. So now I'm going to do your classic object level parent-child relationship to it. So I'm taking the child here, the input geometry, plugging it into a multiply. I'm taking the transform matrix for each particle. I'm plugging that into the second input of the multiply, and that's a parent-child relationship. I've just multiplied one matrix by another matrix, and that creates the offset of each point. That's it. That's all the copy stop does. So now I would extract the point position by extracting my translation And now I've got all my geometry positioned, rotationed, and scaled according to each particle. So this does it really, really fast, and we don't need a copy stop for it. We now have infinite variation on all our rocks using the noise function earlier, and we just transform them into place after the fact. Okay, so that's much faster than copy stamping, and it's also a really nice organized way to do it. All right, so that's something to think about over lunch. We'll explore it a little bit, tinker with it after lunch, and then get on to DOPS. All right, let's do lunch. Questions about this first? Questions? Yep. Who's gonna try this this way from now on? Yeah. Try. Okay. Well, we're gonna get it. We're gonna get it. Once you start doing this kind of a way, it frees up a lot of harder things to do in Houdini. Because I've seen these nasty networks with copy stops nested in copy stops of stamps and arbitrary variables way up the chain, and it's hard to read. This is a very linear workflow, and it's a very fast workflow for simple things like that. Yeah, but yeah, we're gonna get it. This matrix stuff, once you start using it, it'll get a lot easier, and it's so much more organized than worrying about normals and up vectors and you know, oh gosh, how do I do this? One of the hardest things I've done with matrix math in Houdini was wire deformations. So basically on Jack the Giant Slayer, we had to have a forest of trees, and each tree from it was this program called that generated trees that the modeling department used. I forget the name of the program, but it generated a fully fledged tree, and it had a wire inside the tree to represent the branch structure and stuff. So how do you wire simulate these trees? Well, I could have wire simulated one of the trees, but we had a forest of trees, and with 100,000 wires per tree, there was just no way to do that in DOPS. So I had to come up with a little bit faster way to do that. So they had a root, like a base root of just like, it was just like about 40 points. And that's easy enough to do in a wire simulation. So each tree got its own 40-point wire simulation, and as giants banged into it, it would go, and that was the wire simulation. It was really fast, actually. But how do you get all the branches to do what that wire is doing? Because each branch has a different angle to the base wire, and each of those branches have a different angle to that branch. Well, you can actually describe a tree like that in a parent-child rigging situation, but you don't have the luxury of using bones and nulls and object stuff with a geometry wire sim. So I was in a pickle, and that's where I really had to start using this stuff a little bit differently than just hacked routine operations where it was kind of transforming one thing to another. Instead of that, basically constructed a matrix on each point of the wires, and then if it would find the nearest point at the base, and it would just inherit the which point it should get its transform from the which wire it was connected to, and then this 40-point deforming wire would parent-child deform all of these other branches, and it actually didn't need a simulation on the sub-branches. It looked completely natural, and it turned about a 20-hour sim, 30-hour sim per tree into something that looked almost as good, and it was instant. Okay, so that kind of an operation is really hard to think about if without these kind of parent-child things at a geometry level. But imagine rigging at VOPS level. That will really free up your techniques. So a good way to try it out is by trying to understand this kind of a network. Once you get a matrix on your input points and a matrix on these other points, you can do anything you do in rigging to your geometry effects, and that'll make you a lot more powerful. All right, so let's think about that over lunch and come back and play with it. Let's reconvene in about 1:40 like yesterday. I know that sometimes the service takes a bit longer, so whatever we go over, we'll of course make up in the after 4 sort of thing. Okay, so actually, I hadn't given an explanation of this other subnetwork down here. Basically, we've calculated the transform of all these particles and geometry into the right place, but we didn't really address the velocity of what that would be for the motion blur and stuff like that. So normally we just inherit the velocity from the copy stop, right? So we could do that too if we wanted to. We could go into subnetwork in this VOPS network, and we could gather the velocity off of each particle here, v, and we could pipe that into the point velocity, and that would be essentially what the copy stop does. Okay, but the reason I'm not doing that is because there is a better way to do that. If anyone's used the trail stop or just the copy the velocity from the particles, we'll notice that if you spin a teapot 90 degrees, then you get like stuff trail stop going in. Well, I'll demonstrate it. Okay. Polygon. Okay. Okay, so what the trail stop will do is it'll compute the difference between 2 point positions, right? That's good for most things, but the second you get into heavy rotations, especially from simulations, you'll notice that it won't always give you consistent results. So as I keep rotating this, it's going to give me exploding and exploding results until I rotate it, oops, more. Actually, it should be on 1 frame, not 3 frames. Let's see. Okay. So this can be frame 1. And this can be frame. Forward 1. Okay. So, the trail stop will give results as long as it's spinning in a way that it understands, as long as it's going from point position 1 to point position 2. But the second you rotate past 180 degrees, it'll start decreasing again because it's getting closer again until you get back to where it started. In that case, when your velocity was actually very violent and spinny, now it thinks that we haven't moved it at all. So trail stop accounts for positional changes very well, but not for rotational spin. Doesn't account for that very well at all. The other thing to watch out for in the trail stop is that they're not actually at the right angle. They're close enough for most things, but they're actually not correct. If we do take into account the angular velocity, we're actually going to get the correct velocity. And in DOPS, that's called, in the DOP import, that's called integrated point velocity. So when you use integrated point velocities and import your DOP objects, it's saying, okay, what's the rotational velocity? And we're going to do the math on that to get the correct velocity attribute on every point in our geometry. That's based on a few things. You take the center of your object, from which the center that, not the center of mass necessarily, but the center that it's spinning around, and you say, okay, how fast is this spinning? Cool. Now, how close is it to the center of the object? So if it's right at the center of the object, what's the velocity going to be if it's spinning really, really fast? What's that?
It's going to be really high. Or no, it's going to be lower.
Yeah. So if it's exactly in the middle of what it's spinning at, how fast is the velocity going to be? Point velocity.
0.
Yes. Because it's not, even though it's spinning really fast, it's not moving at all. Right? Now, if it gets farther away from the object, it's spinning really fast, this is going to be a point velocity. It's going to start increasing. Now, which is moving faster? My right hand here or my right hand here? This guy's moving faster, right? So the closer I get into this, it's the less it's spinning. The farther I go out away from it, the faster it's spinning, right? So we can use the angular velocity. That'll give us the axis it spins about. We can use the intensity of the angular velocity to say, okay, how fast should this be moving based on the distance it's away from it, and then the angular velocity, we get a vector that determines what that point velocity should be. So that's the calculations I did. I reproduced what was happening to DOP import in this network right here. So this is the math to do it. I've done it, so you don't have to. This was, believe me, this was like a whole day of looking up online math crap and figuring out what equation I should use for it. It ended up not being very bad, but I still had no idea how to do it. So basically, you take in the velocity, existing point velocity of the particle. You take in the position of the particle. You take in the angular velocity of the particle. You get how far away it is from the center. So that's that distance there on your geometry. Okay, so that's the distance from the center. Would be the length, how far it is. Then this is the normal and also the normal of the angular velocity. If you do a tangent there, so this is the vector from the center. The way it's spinning, say it was spinning this way, so that would be this axis. Okay, so it's spinning about this axis. So it's spinning on this axis. This is how far it is away from the center. It's this vector. The tangent of that is the direction that it's spinning. So that's this cross product here creates the tangent of those two vectors. Okay, so then we have the direction that it's spinning. We have the distance from the center, so you'd multiply those two things together. Okay, and that would get the intensity of how fast this velocity attribute should be on these points. Now you'd multiply that by the actual angular velocity magnitude vector, and then so you multiply all these things together, and you get the correct angular velocity. All that's left to do from there is actually add the linear velocity, or the velocity that travels from frame 1 to frame 2 in positional space. So that's all that is required. So that's what that fancy switch does in DOPS, is do the same thing in your particles, and your velocities will be better. I mean, you might not notice them, but if you can get it a little better, why not? So yeah, I encourage you guys to explore that on your pop simulations, on your effect shots, see if it looks a little better maybe. Okay, so anyway, that's everything about particles. I think we're all particle masters at this point. Now let's take a look at some DOPs. So, all right, simple Jeep destruction sim. We'll go into the constraints Jeep destruction sim very soon. I just want to demonstrate the basic idea of DOPS I/O workflow. And I also have an animation asset that we can use too. So let's see. I'll explain what it's doing in just a second. Okay, let's not do that quite yet. Okay, so let's get the ground and the G. Okay, So the idea is the Jeep's driving along and gets blasted by a tank. Okay, if I was driving the Jeep, I'd be driving the other way, right? Not this guy. So and I'm going to pick a frame that I want him to get blasted at. Okay, so in this case, I believe the blast. What frame did I pick? Let's see. Okay, I picked 47. Okay, so this is the frame that the Jeep got blasted at. Let's see, where's the tank that's blasted? There we go, okay. Boom. Now, this would normally be where the dynamics artist, the effects artist would take over from the animation department, let's say, at a studio. So, okay, we've got our animation, maybe go a little bit past, but we're gonna lock the geometry on that frame and do our effect to it, right? So, that's what I've done. I've taken the animation data. I've done a trail stop to get velocities, and I fractured it. Or no, it's not fractured yet. Okay. Just given it a connectivity class and output. So now this here's the complete Jeep geometry. Okay, 47 is the frame that we wanna blast it at. Okay. There's that. Now, here's the digital asset that I want you guys to try out and can do some cool stuff with it. It's very useful on an example like this. It's even more useful with structural stuff. Like say you're breaking a door down, you're breaking a wall down. I've used it on so many different instances, and I've saved myself big headaches with DOPs. There's nothing more challenging for the dynamics artist than to try to mimic structural integrity when there is none. So an airplane, you want to break apart an airplane, it's going to have natural structural components that maybe the wing breaks off really easily, but the body doesn't break apart very easily at all. Maybe if you're breaking a Jeep apart, maybe you know, one piece will fly in one direction, another piece will fly in another direction. So that's exactly what's difficult to do in DOPS, is control all of these things, like where they're going to break on their initial impact. Once the initial impact happens, they're pretty much just flying in the direction they're already flying, right? For the most part. So that's what this asset does, and it's also keyframing, which is scary. All right, so the asset is called, in the destruction tool set, it's called DT Object Animation Fracture. Okay. And I'm gonna connect it to this geometry. I just defaulted it to read the geometry from the op input path and then output. So we can change that to read in whatever geometry you want. Okay, now it's computing. What is it computing? Well, this incoming geometry would have a fracture attribute. The reason why we normally don't animate things on an effects shot is because there's too many things to animate. So if you break apart a Jeep, imagine keyframing hundreds of pieces. It's too much work, right? So what this asset will do is it'll clump them together and make animation objects for you. All right. The way I clumped them was by doing the determining how big a piece was, and if it was big, it would stay the same way. If it was small, then it would get lumped to the nearest big piece. Okay, so that's what happened there. So let me see. We can open it up and view the clumping. Let's see. Allow editing of content. Okay, and let's go in here. And it only has to do these calculations once. So, all right, let's lock that there. Okay, so this is the minimum fragment size. So I had just a connectivity on all the pieces, and if you have a minimum fragment size, it's going to make a lot of pieces for you. So I'm going to raise this. I'm going to say the minimum size I want is going to be an area of 10. It's going to chunk some numbers here. Okay, now it's all just one big piece. So there wasn't any piece as big as 10. All right, so let's try 1. Okay, so now we've got a few big pieces, and this would almost be in the range where we could actually animate it by hand. All right, see, what did I actually choose for my final thing? I choose 0.9. Okay, let's try 0.9. Okay, a little bit to play with here. Okay, now I'm going to say make X forms. And what that'll do is it will create a list of animation keyframeable, what do you call them, handles. So make X forms. There we go. So we've made 16 transforms from this. Okay, I'm going to set a keyframe, the K key. I'm going to go into transform mode first. Okay. Match current definition. It's going to think one more time. Okay, so it's making a transform out of each of these pieces. I'm going to view init. Okay, so going into transform, and I'm going to set a key. No. Maybe this is not the right view mode. Uh-oh. Let's see. Is this being viewed? Display 0. Uh-oh, I think I messed up my if animid is view equals 1. Okay, should be viewing it. Sorry about that. I think I selected the wrong view mode here for some reason. Unless I'm viewing something else that I'm not aware of. Ah, Jeep, okay. Ah, okay, there we go. Maybe it does work, there's hope. Yes, thank God, okay. So, yeah, so we've made transforms, and here I'm gonna set a key. Okay, good. And all of these guys got a keyframe on them. Okay, so they're keyframed at 0 at frame 47. Okay, now I'm gonna go to frame, say, 48, and I'm gonna do keyframe animation. So this is the world, the kind of the global mover. So okay, I'm going to give this truck some forward momentum here, and then I want to actually art direct the there we go. I want to art direct where these pieces go. So we can make this wheel fly out into this side. I'm going to make the bumper fly forward. And these kind of things would give you really good control over where things actually fly, how they break apart. I found that this is, even though it's maybe a non-procedural step, you don't always have to be procedural with Houdini. If you know exactly when you want something to happen and you really just need really good control over it, then this is what this is doing. It's giving you, really good control over exactly how this thing breaks apart under this circumstance. Okay. There we go. Okay, now these would feed into the DOPS simulation. Okay. So once we compute velocities on these with the trail saw, then we just feed that in. All right. So here's the Jeep that I've already broke apart, and it goes from this to that. Okay, so that's my hand animation of this Jeep. Okay. And into the simple Jeep destruction sim. Okay, so let's see what we're doing here. All right, so I'm merging in the Jeep. Okay, so it's just doing two things. It's going from that to that. It's the merging in that asset. It's time shifting it to the impact frame. So now it's just locked, but notice that it has the velocities present from the digital asset. Okay, so I've taken control over exactly how I want it to break. All right. At start anyway. Did not leave that up to DOPS. Okay, now I'm just doing a few, let's see, I'm doing a, promoting the animation ID attribute to a primitive attribute, and then setting this attribute called name class. So just basically just a designation as to each piece. Now, there's been a change recently in DOPS that they use a name attribute for their fracturing. Okay, so we used to have to use groups for that in the RBD fracture object, and that was a pain because it was groups are actually pretty heavy. They go on each set of polygons and they assign a big string to it, and they say if they're in the group or if they're not a group. A single attribute is best because you can't have more than one in a single attribute. In groups, it's presuming that you can have multiple polygons in different groups, whereas an attribute, it can either be in one or the other, right? So here's the name attribute. We went from our name class, which is primitive now, name class, so we go like 0, 1, 2, 3, 12, 15, so for these guys. And then we went to this name attribute by, I called it fract for fracture, so fract underscore name class. So now that means that we have our name attribute saying fract 0, fract 1, fract 2, fract 3 to 15, okay? Now, this is our geometry we're going to go into the RBD sim with. Okay, so what's this mumbo jumbo over here? Well, these guys are the matrices from the animation asset. So there's both a point and then there's the centroid that we animate it to. So from this, we can actually calculate the centers and the rotations and things of that piece of geometry that we're using. It would have the same animation attributes, so we turn that into the same name class as well. So each of these would have their associated point that we get the initial velocity and the initial position from and everything. All right, going into DOPS. Okay. Pieces. So what is our creation frame? Well, I've set that to the frame that we're interested in, which is 47. If this was a dynamic system, you'd set it to $F or $FF. Okay, but for right now, it's just creating everything on frame 47. Okay. Now I'm adding another piece of data onto here, and that is the points from the input here, this guy. So not a lot of people work with DOPS to the point that we feel like we have control over what kind of data we're using. So what this is doing is it's taking all this data here in details view. Okay. All this data here, and it's adding on an extra piece of data. It's that point at the correct rotation. Okay, so it's got its rotation, it's got its velocity, all that stuff. Okay, so when I add that on, it adds on this piece of geometry data right here, transform points. Okay, there we go. And here's another little trick for those of you that are interested. It's always nice in POPs to be able to tell how long something's been alive. That's what this guy does in DOPS. So it's just making empty data, and it's applying the simulation frame minus the frame the object started simulating on. So that'll give a life out of DOPS. As to if you do particles of DOPS, you want to know probably how long it's been alive in case you want to kill it or do some time-dependent thing on it, life-dependent thing on it. So that's what that is. So I'm just applying that there. And that's over here in info. We have that as well, that D-life, active time. There we go. Okay. Now, I'm initializing the motion. Now, a lot of you guys have probably done it this way, where we take our RBD fractured object and we say inherent velocity from point velocity. And that'll work here. It just won't be quite as good as actually using the rotational velocities and the positional velocities. If you use a trail saw and you gather your geometry stuff from that, it's only going to be able to spin a certain speed and no more. If you use angular velocity on points to control how fast it spins, you can spin it a lot faster if you need to. So here I'm initializing it with a motion DOP, very similar to what we just did in particles. The same way, if it's the start frame, then initialize it with this channel, and this guy is using its data path to get the angular velocity. And if it's not the simulation frame, simulation start frame, then just keep the current velocity. Same with the angular velocity. So this does exactly the same thing we did in POPs. Same thing with the drag. Same thing with gravity, and we're solving the RBDs. So we've taken that animation we did on that one frame, and it only took me about, granted not working on a movie, but it only took about 10 minutes to animate those objects to get them to fly out in that direction. So we animate that, and we get stuff flying the appropriate ways that we just keyframed it. Okay. Now I'm not using bullet yet, it'd be faster if I was. There we go. So they're spinning the right way that we animated them and told them to spin. Okay. Now, here we have the ground, and that'll get created on the first frame, I believe. Yep. And we have a little trick that I've had to pick up over the many DOPS things I've done, where colliding with an object, a deforming piece of geometry, wasn't good. Okay, who's actually read in a DOPS piece of deforming geometry and used that collide with? How was that experience? Really slow, huh? Really inaccurate and slow, all that kind of stuff. Okay, this is an RBD point object. It's gathering the point from the tank. So either you can read this data from, like, say the animation department gave you a tank to collide with. They would have a transform for that tank somewhere. Okay, so they could tell you, export this animation channel for me, that sort of thing. Or you could figure it out on your own. You could use the start frame, and you could determine if it's a rigid body anyway. You can determine the offset calculations with it. Basically, whatever you can do to get transform information off of this piece of geometry. Okay, once you have that, so in this case it was easy because I actually made the asset myself. But so once you have that, here I've got my normal and my up vector. I'm gonna merge these points. In this case, it represents the bottom of the tank and the two guns. Okay. Once you've got that transform information present in a normal and an up vector, as you're used to doing for the copy SOP, then you can use an RBD point object to collide with. All right. So an RBD point object only has to initialize its collision geometry once. And then it gets really, really good collisions off that collision geometry because it's already it knows how to transform in DOPS. It doesn't take any time to transform or compute it either. So if we look at this, I'm going to merge these tank points with my RBD point object. They have the path to the geometry on them. So if we look at the spreadsheet here, I've got my instance attribute. It goes OBJ tank bottom, OBJ tank top, OBJ tank gun. That'll tell DOPS what geometry to use for it. The normal and up will tell DOPS what its transform should be. And the, let me see, velocity, if you have it, if it wasn't a static object, it would, it would be thrown in that direction. But we don't care about that right now because we're using it as a static collider. Okay, so here we go. Here's our RBD point object. Here's our point SOP path, just the input. I am not creating active objects. Okay, so they're not active. It means they're not going to be rigid body simmed. Okay. Now I'm using the point position DOP to transform them. So I'm using the point number of OBJ. That's the processing point. So if it has 3 objects fed into it, it'll process 0, 1, 2. If it has 5, it'll process 0, 1, 2, 3, 4. And that's perfect for grabbing the point. Okay, so here's the SOP path with the points. Here's which point it should grab. Now it's rotating it to the normal, and I am updating the time on every frame, set always. Okay, if this is set initial, it won't move. But if you set always, it will move. Okay, so looking at this, I wonder if it'll move right now. Let's see. It might not because I haven't solved it yet, but yeah, it's moving. That's pretty fast, huh? Instant playback. This will give you really, really good collisions. All right. No playback speed necessary. No computing volumes necessary in every frame. Okay, so we mix that in with our RBDs. We just kind of collide with the ground in the tank. And this is how I would set up a bread and butter DOP simulation. Now, so yeah, we can take a few minutes and experiment with the rigid body sim. Now, this is also something that we probably understand more after we start using it a few times and everything. But from here, who has worked with a studio solution that automates the process of exporting geometry from a simulation package? At DD, for instance, we had drop, so we wouldn't export geometry, we'd export points. And then we'd transform the rest geometry according to those points. So who's worked with a system like that? Just Alex, huh? Okay, so basically, you don't want to be writing out geometry out of DOPS. That's bad. Why is that bad? So here I'm using the DOP import, and it's writing out, say I'd cache this to disk. Okay, so who can give me reasons why that isn't good for production?
Heavy.
Yep, heavy, that's the main thing, I think. It's a lot of data on disk, right? What else? All right, well, once it gets out of here, do you have any control over it? Like, what if you wanted to update what if you wanted to put a crack in the geometry after it was simulated? You'd have to resim it, right? So that's the main disadvantage right there, is that if you update the geometry, you have to resim, okay? Because it's moving, so how do you get different geometry on something that's moving? It's just arbitrary point data now. So how do you apply that to it if it's already cached to disk? You can't. So that means a resim, and if it's heavy, you're looking at a long night. So what studios often do is they will only cache out a point cloud, and they'll use their proprietary tools for it. So here, instead of exporting the object, we are reading this XForm points template. We put a point for every object. Okay, so hello, let's cook. Okay, here we go. So here's the transform points that went into it. Let's go. Come on. Okay. Okay, so here's the points that went into it. And then those points will get transformed by the geometry data in this digital asset. Should see him moving here in just a second. There we go. Okay. So if we compare what's happening to the geo import, we can see that there's a point representing all of our objects here. It has the correct transform on it. The way I'm doing this is I'm using I'm creating the number of points by import records, and just moving them according to that information that's already present in the fields and dops. So it's pretty simple, just copying data onto the points. Okay, so you can use this digital asset to do that. All right. Now, once we have those points, it's really easy to transform our geometry according to that. So yeah, get rid of this details view here. I think it's slowing us down. Come on. Okay. Okay, so here's our static geometry that's not changing. Once we import our simulation points, is caching on? Yep. Then we can do whatever we want to this geometry. So we could apply a noise on it. Let's see, like say point jitter. Okay, and it would still, let's say we'd already written our simulation points to disk, it would still transform them the way they should. And we can see a common theme as we're doing this both in pops and dops, is that we want to have control over the geometry, and then we want to represent the simulation in the simplest form possible and then transform it later to that. So there we go. I don't know what this guy's doing down here, but yeah, that's what the simulation did anyway. Okay. Yep. So yeah, anything we write out here, we can do whatever we want to it after the fact, whether it's up-res it or put fractures in it. We could animate fractures in it as it hits the ground from there. Basically, we just want to have a separation between our points we're writing out to disk and our geometry that we're going to use to render with. Okay, and from here, I'm using the same velocity calculation as we did with pops. Okay, get rid of that funky point jitter. And there we go. Okay. So it's the same exact thing as the geo import will give us. The only difference here is that we're taking control of the reading and writing process. Okay, so let's spend a few minutes and go through this system, maybe redo the animation a little bit. You can try the bullet solver out too. It works the same, only a lot faster. And after that, we'll get into some constraints, which is a little bigger network here. Okay. So let's just get the idea first with the simple Jeep destruction sim. Questions on just the basic DOPS I/O process and any questions on that?
Does DOPS not calculate velocity well on its own?
Oh yeah, it does. So if I were to do the geo import, I would do integrated point velocities.
Oh, do you almost always do that?
Yep.
Okay.
Yep.
So that's not on by default.
Well, if we wrote points out to disk, we wouldn't have that.
Right.
So we'd have to come up with our own way to get those velocities on there. So that's what that is. So you can get the velocity off, but once again, we're stuck with a single velocity on each. Integrated point velocities, we have velocity and angular velocity present in V and angvel from the DOPS fields in each RBD object. So all I'm doing here is I'm reading them onto these points.
Right. Okay.
And then from there, it's the exact same way our particles worked. We were using V instead of vel. We were using W instead of angvel, but the process is the exact same.
Cool.
Yeah. Okay. So yeah, we'd start with our rest geometry, the geometry that went into the sim. Oh, manual mode. We would transform those by the points that were presumably written to disk, and then we'd put the velocities on them. So let me view the velocities here. Okay, so these are still the velocities that were in the trail stop from the animation. Okay, so we calculate the new velocities. So it looks like that guy freaked out, but whatever. Yeah, those are the new velocities on the points. And this will be identical to the geo import. See, point. And all this does is it sets the normal up an instance. So this is where the tank geo gets created, is the point instance.
Oh, okay.
So on this point, we're pointing it to the geometry of obj tank 1 tank bottom. So that's the geometry. And then the transform at object level would be that.
So you can instance into sims?
Oh yeah, the RBD point object, that's what it does.
Oh.
So it uses, for the default behavior, it uses geometry path, use point value. Now you could override that. So you could put it to whatever geometry you wanted really. But I like to follow the workflow and just use my instance attribute. And the most notable time I recall doing this was on Mummy 3. I made a dragon out of this. So the Mummy 3 dragon was a 1,000,000 polygon mesh, and I was supposed to collide with this thing to break walls with it, and I only had 2 weeks to do this shot. It was already out in China already. So you know, I couldn't afford the time it would take to collide with this. They were even changing the mesh as we were working on the shot, so there's just no way to, especially like 6 years ago, there's no way to, you know, do that kind of calculation in DOPS. So I had to come up with this kind of a system to do that. So what I did was I made a cylinder, and then I put cylinders in the dragon, different sizes, and a point on each of the cylinders. So it would use UVs to keep, like, so say there was a cylinder in the middle of my body here, so I'd have a point here, a point here, a point here, and a point here, and that would give the orientation for each cylinder. So I'd cache those out, and then I'd have the point in the middle of it that would have a direction and an up vector. So I had the dragon basically inverse rigged to where it had a bunch of cylinders in it. So the RBD sim would collide with these cylinders, and it was instant. And I just have to cache it out on the farm, but then I'd have my point cloud with the cylinders, and I didn't have to worry about it anymore. So yeah, anytime you have really complex stuff to collide with, set up a system with the RBD point object, and it'll turn slow dops into fast dops. And I did that for the Giants on Jack the Giant Slayer as well. It had an automated system that would just put balls in the Giant's limbs, and they would collide with the forest as they ran through the forest. Yeah. So, okay. Good question. All right, so now I'm in the demo, and yeah, these are things we can dive into at home, and if anyone gets stuck, just send me an email. So this is the constraints Jeep destruction sim, and obviously I wanted to give everyone with how difficult constraints are in DOPS. I wanted to make sure that everyone understood the workflow of how to do it right. And I had to figure that out too, because I was used to using proprietary tools at Digital Domain to do that. Now that DOPS has Bullet, it has a good constraint system. Whew, it's actually better than DD's DOPS or drop thing. So yeah, constraints and DOPS. I'll just kind of step through the nodes here and show everybody what's going on. And I'll remember myself what I did. Okay, so once again, I'm merging the animation into my network, and I'm fracturing them now. So I'm looping through each animation ID and fracturing it with a Voronoi fracture. Yeah. The reason you want a Voronoi fracture with constraints, particularly in DOPS using Bullet, is you don't really want to have to contend with concave geometry. It's not worked out yet. I think they're improving it on every build, but it's really not very good at colliding in, especially now with constraints on it. Okay, so just simple Voronoi fracture, and it'll take your problems away. It's more than fast enough for a lot of things to use more pieces as opposed to one concave mesh. Okay. Okay. I wonder what it's cooking now. Oh, it's cooking one particularly nasty piece. I remember that from my laptop at home. Whenever I've had to fracture things like Jeeps, airplanes, things like that, Voronoi is not a perfect process. So if you do try to fracture something and the point's just a little bit off, you get all these like crazy rounding errors. Sometimes waiting, it will work itself out. Sometimes you have to choose a new seed. And that's just where technology's at right now, unfortunately. Voronoi, the benefits of using a Voronoi fracture outweigh the negatives, but the negatives are that your scene might cook forever. Okay, so you might have to, one test I like to do to see if my Voronoi is defective or not is I'll make 20 fractures all at different seeds, and I'll send those to the farm, and whatever's done in the morning, yeah, it'll be what I use. I'll remember what the seed was to fracture the right thing at. Okay. This worked the first time though, so it doesn't happen often. It just happens more than you'd like. Airplanes are really bad because they've got those really thin wings. So I do that in the Ender's game a lot. Fracture the airplanes. I was like, oh, it's not fracturing again. Yeah. Okay. Does anyone have any tips for fracturing stuff with Voronoi, like really difficult geometry?
If you Voronoi is way deep in there, you can get better offset and shape sizes.
Yeah.
That took me forever to figure out.
Yeah. So you do like a really good volume first, right? And then put points in the volume.
Yeah, I mean, just to get variation. Otherwise, it's just like I had the problem where I wasn't having enough large pieces mixed in with medium-sized pieces with smaller pieces around them.
Got it. Okay, so here's our fractured geometry. All right, and we've got a lot of we've still got the animation ID present, but now it's got this extra attribute, and the small, I've designated what the small pieces are as well. Okay, here's a connectivity class, and this is that chops trick I was talking about. Okay, basically I wanted to renumber this because I fractured everything. So by animation class, or object that we animated, I fractured that. Then I went on to the next animation class, fractured that. Then so what that did was the attributes that were used for the fractures start over. So they go 1, 2, 3, 4, 5, and say I had 10 pieces, it go to 10. Then for the next piece, it would start over and do that attribute again. So what this digital asset does is it'll renumber it. Okay, and it uses chops to do that. So basically it lays the attribute out on a grid, and then it counts each difference in it. And then that'll go from this to every time it changes, it'll just do a new one. It'll start over it at 1. So if anyone's curious after class, I'll explain what kind of madness is going on in there. Okay. Let's take a... I'll view a motion view of it so you can see. Here's the original attribute. Oop. Here's the original attribute. So you can see it's all over the place. It's got different values, different things. Okay, and then I'm just triggering it every time it changes. So it starts at 0 and goes to 1 after that. So that's how you easily reorder any attribute. Use chops. That's really good for that. Okay. All right. Okay. Now clustering. Clustering is necessary for constraints. It really is. All right. So I made an attribute called cluster, and I'm just visualizing that to make sure it's okay. Okay, so these are going to be the pieces that I use to the sub pieces. Okay. So there's going to be cluster, and then an attribute for each individual fracture, each individual connectivity called subcluster. Okay. I'm sorting just so I have even points, pretty much. It goes from like 0.0 to 0.1, 0.2, all that sort of thing. Okay. Now I'm setting that name class attribute that we did in the last dops thing. It's just a numbered designation as to which dops object it'll be, and then the name attribute, same as the last one. Okay, now whenever you do a complex fracture, and especially when you're fortunate enough to use like a point-based system, I would always recommend caching out the fracture. And you don't have to cache a lot of geometry to disk. This would be the only geometry you cache to disk, would be the result of your fracture. That way you don't have to refracture it every time you do your scene. And we don't have to write it out on every frame, because we're using these attributes to keep track of where our geometry should go. Okay. So here's my final geometry going into here. Okay, it's not time dependent. I can scrub all day, won't change. All right. Now, here's where I've just done a simple VOP to multiply the velocity. Okay. Converting a name attribute to a point attribute. I'm creating those transform points as I did in the last example. Be a few more this time. But this would be an actual studio application of a complex destruction shot, so we can expect to be dealing with lots of points. Yeah. Okay, so there's all the DOPS objects that we'll have in our DOPS sim. Okay. Now, there's a really cool node that I learned about to do DOPS constraints, and I'm thinking that I could use this node a lot of other places. I just haven't yet because I didn't really know about it. It's called the tetrahedralize. Anyone already know about that node? Yeah, it's pretty cool. So it will do this. It's stuff. Pretty neat, huh? It'll draw lines from each point to each other point. So there's got to be lots of uses for that in effects. I haven't thought of any yet, but it's definitely good for constraints. Okay. Now the advantage of drawing a polygon spline from from one point to another is we have a name attribute on this point, we have a name attribute on this point, and these points are different name attributes, but the line is a primitive, and the primitive attributes store the strength and the time it takes to break and things like that. Each name attribute on each point stays as a point attribute, so it controls what object it's constrained to, what object it's constrained from. So that's how constraints and DOPs work. I've got a really simple DOPs constraints example up here, and all it does is a single constraint. So if anyone's really wants to study the nitty-gritty of how a constraint is set up in DOPs, just look on this thing. It's got all the attributes on the box and the sphere and this line to reproduce this process that I'm using the tetrahedralize SOP to do. Okay, so we've got our tetrahedral. So I looped through each animation ID, and I made a separate tetrahedralize out of each one, out of each DOPS points. So all these DOPS points here, separate out each animation ID and do the tetrahedralized loop to them. Then we have the brand new Houdini node glue cluster, and it's a digital asset, of course, like many new Houdini nodes are. So it sets these attributes on them. Now they made a mistake in this one. It gives you an optional cluster attribute, but it doesn't actually take anything but a cluster attribute. Okay, so don't change that. So you have to have a cluster attribute going into it right now. Alright, so what the glue cluster does, and here's a visualization thing for the glue cluster. I'll go ahead and just copy this guy to show. Okay, so there's internal strength and there's cluster to cluster strength. The internal strength would be this guy. So cluster to cluster would be this blue bit to this blue bit to this red bit, though these are separate clusters. The internal strength would be the connectivity SOP. So each separated piece, that'd be the internal strength. So I'm making a cluster out of each of these, and then all these nuts and bolts would be internal. So I'm not going to break those apart as often. So you almost always want the internal strength to be higher than the cluster to cluster strength. Okay. All right. So here's our CD test here. Okay, so internal strength would be, I thought I already adjusted that. Oop, it's not finding something. Oop, there we go. Okay. Okay, so internal strength is these connections. Or sorry, yeah, no, that's right. Each piece to each piece of the connectivity. The cluster to cluster strength is each big piece to each other big piece. Okay, and over here in glue cluster, I've just set those. So I've set the internal strength to 3000 and the cluster to cluster strength to 50. And I thought those are pretty good values. Believe it or not, it is fast enough to test with now. Previously in DOPS, you turned on constraints, you used the default engine, and there's no way to test with it, let alone get a shot to work with it. It's just too slow. Now it's easily testable. And if you ever really want to test out the strengths, what I'd recommend is isolate a single piece of your cluster first. So when I did testing, I tested with a separate animation ID. Should cook any second now. What are we doing? What are we doing? think that might have been the bad piece. Sorry. Question so far about clustering. Has anybody clustered or done any like constraint setups before with anything? Okay. It's a bit to get your head around at first because it's logic that is too much to look at. So you really do have to rely on the computer to make those connections for you, unless of course it's like 3 pieces or something. But the way to control your clusters is with loops. So for each loop is an easy way to isolate each thing that you never want to be connected. So say I never want this big attribute over here to be connected to this other big attribute. Just do a loop for each attribute as you make your cluster connections. Then it's guaranteed never to form that primitive to the other side. Okay. Then in terms of clustering and subclustering, sorting is a good thing. Okay, so use the sort SOP, and you can also try out that tool digital asset to resort things, and that allows us, like, keeping point attributes in a nice organized way is really necessary for like keeping the SOP simple is necessary for when the SOPs get complicated, because if the string is messy going in, then it's going to be really messy trying to actually cluster it. Okay, there we go. So that's finally done, I think. Where is our cluster? Give me a cluster, any cluster. Okay, come on. There, okay. Yeah, that must have been the bad one. Okay. So, yeah, here's our glue cluster. And so what I've done here is I've done the geometry going into the first input just like before. We have our transform points just like before going into the second input. The third input is now reserved for these new magical clusters. Okay, now the clusters must correspond to the object names, otherwise they won't work. I mean, obviously it needs to know what to constrain to what, right? I find that it's better to implement a point system in your DOPs because points are a great way to keep things straight. So if we already are in the habit of using points for DOPs, then clustering is actually quite a bit easier, and it's harder to make clusters directly out of geometry. Okay, so now we've got these clusters going into the third input here, and our previous tank into the fourth input, our RBD point colliders into the fourth input. Goes without saying we can have more than 4 inputs, we just have to reference them. Okay, so let's try it out. Now, this is using the bullet engine, okay? And it'll take a little bit to initialize, but once it initializes, the sims just fly. They're a bit slower with constraints, of course, but it's really fast. Here we go, so it's starting to take off now. I did another little trick in this shot, in this setup. I threw a bunch of balls out of the tank. Now, the reason I did that is because it gave it a really realistic sense of tearing apart. So you can add things that aren't actually there and enhance your effects. You don't always have to rely on the velocities that you are going into the scene with or anything like that. Sometimes it's great just to throw a bunch of heavy balls at something and look at what it does to the simulation and the impact. And what's a good way to generate heavy balls out of a tank blast? You have a tank blasting system with our points and our normals that we use in our setup. Okay, so yeah, this is just flying. This used to be undoable a few years ago. Now it's actually just flying on a single Windows machine. Okay, pretty cool, huh? All right. I think I turned off caching for that one. Okay, so now using our simulation points import, we would get the points back out. I'm just reading the cache data here. It plays a lot faster in the viewport if you just make one particle system for it instead of a lot of them. But yeah, so just reading the points out, and instead of representing heavy geometry with all of our stuff, we're representing it with a point cloud. And from there, it gets transformed back into place the same way we'd transformed it before. Alright. We also have really good velocities on it because we're using our velocity network that we talked about. So, integrated point velocities. Alright. So, that is the demo of constraints. There's another little network that I encourage you to explore over here, which is particles off of collisions. So often you'll get a lot of awesome detail from using constraints in your sim and fractured pieces and stuff, but you want that extra bit of detail for the producers and the effects supervisors to say that's real. So for that, you'd want changing point counts and stuff just spitting out in controllable directions. And a great way to base a particle system off of a dynamic sim is by impulse. Does anyone know what impulse would be pertaining to this stuff? What is the difference between impulse and velocity? All right. So velocity, we get a remote control and it's traveling. Now it's traveling at a constant, right? So say these keys are really loose. If I was traveling my velocity at a constant, would the keys fall out? Right? Probably not, huh? Okay. So what if I did this? The keys were like loose and then I went doop. Well, the keys would probably keep going, right? If they're really loose, they'd probably fall out. What if my remote control went like this? They each came to an abrupt stop, and then it bounced back a little bit. That would be a really high impulse value because it went from all this motion to a direct stop. That's when particles would come out of your objects, is when an impulse happened. Not when the velocities are high, but when you have a high impulse. An impulse is a change in velocity. Velocity is a vector, and impulse is a change in that vector. Okay, so to get the impulse off of our RBDs, let's see, I'm merging in my DOPS points. Once again, a great reason to cache your sims out as points is because you don't want to be dealing with heavy geometry. You want to be dealing with points. And from there, I'm just calculating the impulse. That is done by the change in velocity. So I'm going velocities, f-1 velocities. I'm just calculating the dot product between those two things. That'll give me the impulse, I think. Let me see if I can make it. Velocity. Oh, I'm subtracting them, not the dot product. I'm just subtracting them from each other. So the change in this velocity to this velocity, you subtract that. You get the length of that. That's how big your impulse is. Okay. So base your stuff on that, on impulse. So now we can see as I play through this, we'll see the impulses happen when they hit the ground, right? So watch that wheel. It's going to go wheel, 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 wheel. Boom, it well, didn't really do much there. Let's see. Let's see if I can flipbook this out just to show. When the wheel hits the ground, it has a high impulse. try that. And watch that wheel hitting the ground. Boom, high impulse. We didn't even have to get collisions out of it. We're just going to say wherever there's a big impulse, throw particles out of it. You'll get the correct velocity of the particles because it already has the velocities on it, right? We just need to know when to shoot particles out, and that's based on impulse. Okay, so getting the impulse, setting the attributes of impulse by name class. Okay, by that attribute that we use to keep the dots straight. So match by attribute, name class, and then just scattering points on those. So if there's a big impulse, it would scatter a lot of points on it. If it's not a very big impulse, it wouldn't scatter many points on it. And simply use those points to emit particles from. Your geometry will already have the correct velocities on it. So we can just multiply and randomize that velocity a little bit. But yeah, use a scatter stop, get your impulse, and just throw particles off your geometry. That's the great way to do throwing particles off of any dynamic sim that you run into. Okay, so here's the particle sim. Okay, see as the wheel would hit the ground, we have our particles bouncing off the wheel. And then we do the particle techniques that we learned in class and put junk onto the particles. Here's a pile of junk. So often when you're copying junk onto particles, you use junk from the actual thing you're destroying. And the reason for that is if you're in a studio situation, it already has lighting attributes on it, texture and UVs and everything, so the lighting department will never know that it's new geometry. They'll just pass through their pipeline like it was the original mesh. Okay, so I brought in these pieces from one of my ID fractures, and then I just looped them to put them in the middle. Okay, now this resembles an awful lot like that other system we learned, right, where they're all in the middle. So I think I have like 10 pieces here or something. Now, this would be a situation when we'd probably want to go to the copy stop, right, and copy these pieces onto these. But when we have to still go back to what we were used to doing with switch stop and things like that, no. We can use a for each loop and avoid the switch stop. What I'm doing here is I'm making a random attribute for the amount of classes are present in the input. So every attribute on each point has, if the spreadsheet comes up, there we go. Okay, it has a thing called rand on it, I think. Is that what I called it? No, I called it class. Okay. Class. There we go. Class. Okay, so what I did was I just did a round, and generated random numbers between the minimum class and the maximum class. So each of these points have one of the classes present in the geometry on it. All right, so now we would loop through each class of points, all right, and copy pieces of geometry onto it. So here's our original geometry of the points. Here is the piece of geometry that'll be copied onto it, and then we use a copy stop and put these pieces. We're not using stamping because that would take a long time. We're just copying each of these pieces onto those points in a loop, in a for each loop. So now we still have 20 variations of pieces. We just we used a for each loop to loop through that instead of a stamp operation, which had to switch each time. This only switches 20 times for 20 pieces. Okay, and calculate velocity the same way as before. And those are our final particles in addition to our simulation. So that's a really useful thing to add to adopt simulation is secondary particles, secondary braking. Actually, it looks just like secondary braking. And so they call it out and say, oh, is it have subfracturing? They love that word, subfracturing. You say, no, like why not? No, you say yes, and you can see the particles coming out of the piece. It'll break, and then you'll see other little pieces coming out. That's subfracturing, right? Just trick the eye. Okay, so simply merging these together, and that's our final complex studio-ready .sim. I encourage you guys to explore that. Try your own variations. I've included other geometry in this, like airplanes and helicopters and stuff. So you can, if you're putting together a demo reel, try to blow those things up, that sort of thing. Okay. Now, I'm going to spend another 10 minutes and let's look at some pyro. And actually, let's look at some dust. Okay, I'll be quick. All right. So, ground interaction Jeep dust. That's where you're going to find the dust. Okay, and this should be pretty fast simulation because we're using clustering. It was a hard task to remove shelf tools from this equation. All right. So here I'm merging in points from the Jeep driving across the ground. Okay, let me hide the other stuff here. Jeep animation fracture. Okay, let's show Jeep 1. Let's make sure it's okay. I've got some good playback. All right. Okay, so there's a digital asset that will allow you to do any type of ground interaction, and that is the it's in these guys. Ground interaction calcs. Okay, so this is an asset I originally made at Digital Domain, and I've recreated it and made it better for you guys. So what this will do is it'll take in any terrain, it'll take in any object with a velocity attribute, and it'll see if the velocity, the distance, and the angle of the velocity are worthy of a spot on the ground. Okay, so you can adjust the angle tolerance, meaning is it going down? If it's going down, then yes, it'll make something. If it's going up, you wouldn't want it to collide, right? So if a giant lifts its foot off the ground, you don't want it to kick up dust. If it pounds its foot on the ground, you do want it to kick up dust. Okay, so the velocity is angle tolerance. This is the magnitude tolerance. If it's a light hit, don't do anything. If it's a heavy hit, then make some particles. Okay, and distance. Is it close to the ground? Is it far away from the ground? This doesn't actually need any collisions. It just goes based on those three criteria to determine whether something is interacts with the terrain or not. Okay, so yeah, go ahead and explore that. The setup's pretty easy to follow, and it makes some particles off of the Jeep here. So we're going to use these particles to create our dust with volumes. All right, so clustering. Now this is a different kind of clustering. There's a cluster points attribute in SOPs. It's a new attribute as of I think Houdini 11 or 12, I forget which one, and it's a bit of a monster. But what it basically does is it divides points into groups. This was hard to do before. Okay, so if you're talking about something like this, I've divided based on an attribute frame. So if all of these attributes have a frame attribute on them, these are the earlier frame attributes, these are the later frame attributes. See how they're different colors like that? So it's divided it into 4 clusters. You could also divide them based on position or velocity or things like that. So in this case, it's divided it into 5 clusters by frame. All right. Now, it also creates bounding boxes for you. So if we switch to boxes view, we can see the bounding boxes it's created. But those are represented not as boxes, but as these things called average points. And they have the scaling of the boxes as a scale attribute on each of these points. Okay? So, so I'm going to do both, output both. It's outputting both the averaging points and the cluster points. Here I'm isolating the cluster points. I'm isolating it by the current frame. So it's only going to display the points on the current frame. I'm putting a density on it. In this case, it's just the blank value of 10. And doing the fluid source attribute. Who's used fluid source? Yeah, I figured most guys would have used that. So the way to control this fluid source with stamping points is definitely to do clustering into this. Okay. We've also got some random noise on it too. Okay. Now, here is the bounding box points. So I'm isolating those on this other side. I'm saying for each bounding box point, set it to the minimum frame present. So what that means is each of these cluster points would have a frame attribute on it, and it would have a lowest attribute, right? So how do we get the minimum attribute out of a cluster of points? We've done this a few times in this class. It's a old school node. Attribute promote, right. So if we want to get the minimum of all these frame values, use attribute promote minimum. And that way we can assign, since they both have the same cluster attribute, we can assign the minimum frame that the cluster should appear on based on the minimum frame present in our points. So that way the DOP-Sim knows when to create the cluster and save time in simulation. Okay, so for each bounding box point, loop through and set the minimum frame with an attribute promote, and set the frame based on that. So now I'll ISO the frame, and the cluster will appear at the first time that it's necessary to appear at. Okay, same with the source. We've got our source driving around, and I've got partitioning on set to cluster. See, it's going to use that cluster attribute that is set to divide them into different volume names that the DOPS clustering will pick up on. All right, and then you got the ground. That's self-explanatory. Okay, so now into the DOP-Sim. Simple. Woo, what a relief, huh? So we've got a smoke object going in here. We've got a resize fluid container with the delay frames of 2. The delay is necessary so that it doesn't collapse too soon. All right, we're going to give the smoke some time to expand. All right, and then we've got the source volume sourcing the density out of the first input. That's all we really need. I'm going into a pyro solver and colliding with the ground from there. Now with clustering, this will be really, really fast. If you're going to try to do this without clustering, this would be an all-day sim. If it didn't crash your computer. So here comes the first cluster. Oh, I should mention you have to set the creation to continuous. There we go. Second cluster should come around pretty soon. Okay. And we got some groovy dust happening. All right. And this creation here, continuous creation of cluster points. So the clusters will appear and then they'll resize, and that's a really good optimized fluid sim off of anything that you're trailing on. Okay. So I think I did not cache these out because I didn't want to take up many megabytes for our scene files, but if you explore them at home, you can just simply cache them out here to your folder. Okay. Here I'm visualizing it as brown. Okay. On to Pyro. And believe it or not, Pyro is a relief because it's the simplest thing we're gonna do here. So, Jeep Pyro Sim. Okay, not a bad network. Merging in the points. And this is all yet another reason to have points as you cache out your dynamic sim data. You don't want to be doing this to geo. Frame attribute and looping through the frame range. Okay, so you guys remember how we loop through frame ranges on stuff? All I'm doing here is I'm looping through $FF, really. There we go. So it's just a time shift set to the iteration. Fstart to Fend and merging results. So that's just a simple way to cache out everything into the scene. There we go. What have I done? Okay. I hope it's not trying to refracture it. Shouldn't be. Okay. So I've cached out the whole frame range, and as with these DOPS points, they have a common class on them, right? So for that, I'm going to kill the particle primitives and put on lines. Okay. So now we have this really cool alien life form that we're going to do a pyrosim off of. Okay. Density. Now, density for pyrosims is a little bit more tricky thing. So I always just set it to 1 as I was doing the dust sim or the other types of sims. But here, we want to actually do some art direction on that. So here's our density ramp, and based on the frame number, so I'm importing the frame, all right, of these guys, and we're going to control what frame range the explosion happens. Okay, so it's going to feed fuel and temperature in at this frame range. From the start of the frame to frame 59 is what I came up with. And we use a ramp to control how much fuel gets spilled in over that frame range. All right, so now we've got this very controlled explosion. And we can isolate the extraneous stuff, and we're only left with the important density. It already has the velocities on it, because these are points from our dynamic simulation. Okay. All right, so now isolate that by the frame. There we go. And this will be feeding in source fuel into that. Now, I always do a test to see if my animation is working, my noise is working. So I've locked the timeline, I've locked the frame range, and now I can see how it's animating. Okay, is that animating sufficient? Yeah, okay, so it'll give us some variation as it starts to explode in the fuel distribution. Now, this guy is creating the fuel. It's got some noise on it. I've done a separate one for the temperature. It's the same exact setup, same sample distances referenced and everything. It's just that I'm doing temperature instead, and it's got a different noise offset. It's got an offset of 100 here. Why would you want the fuel and the temperature to be different volumes instead of the same volume in a pyrosim? Anybody have a guess at that? Yeah, because if you have the fuel in the exact same place as the temperature, you're going to get these puffy formations. If you have two different noise patterns that are intermingling with each other, then you're going to have this nice catching on fire effect that's more natural. Okay, so that's a trick that I've had to use for ever since Pyro came out in Houdini, is to break up the fuel from the temperature. There's a lot of things of setups that put fuel and temperature in the same fluid source. I recommend different fluid sources for those. Okay, so source fuel, source temperature going into the same node here. Okay, so now we've got a volume with fuel, vel x, y, z, some curl noise on that. As well as the velocity that got from the DOPS simulation, and temperature. Okay. Now we have a bounding box. Now this little formation here is a great thing to form a bounding box out of too. You know kind of how big your explosion is going to be already, and now we would just scale the bounding box up a little bit to account for the rise in smoke and the dispersion outward, and do our pyrosim. Pyrosims in Houdini are multi-threaded. Thank God. In Houdini, on Sucker Punch, it wasn't. I had a rough time with a single processor Pyro on that, but now they're multi-threaded and I'm happy. So the simplest DOPS network we've done, it's 3 nodes. We've got our smoke, we've got our source temperature going in the first input here, and we adjust the settings to get good values here, and then all the just play with the settings, start with the default, add shape as you go, final stages, add your shape, and you'll get some good shapes. Let's do that. There we go. No shelf tools were used for this. Alright. There we are. Okay, so and then in terms of visualization, you would, if you really wanted to render this, we would choose the Pyro preset and it would populate our, that didn't work, pyro, and it would populate our .io with the correct fields. For visualization in the scene, you can import the visualization field from your smoke. And here I've just referenced that to make sure it showed up well in SOPs.